Boa tarde a todos. É com grande prazer que a gente vai fazer a introdução do Bruno Gonçalves. O Bruno é um cientista na área de Data Science. Atualmente, ele está no Centro de Ciência de Dados da Universidade de New York, Estados Unidos. Ele tem trabalhado muito com grandes volumes de dados para tentar fazer análise do comportamento do ser humano. E aí ele tem trabalhado com bases de dados do Twitter, da Wikipedia, do Yahoo também, e ele tem tentado buscar fazer análise do comportamento de seres humanos, de indivíduos, não é? E as principais aplicações dele são na área de linguística computacional, information diffusion, difusão de conhecimento, e também mudança comportamental. E também um tópico muito interessante é a análise de epidemias, né, do spreading, né, de epidemias. O Bruno, ele é autor, apesar de ser jovem, muito jovem,
não tão jovem quanto parece.
Ele é autor de mais de 60 publicações importantíssimas na área de Data Science. Tão importantes que ele tem mais de 4.800 citações no Google Scholar. Então, realmente é uma honra para a gente estar recebendo o Bruno aqui. Agradeço, em nome do departamento, por ter aceito o nosso convite. Ok?
Com todo prazer.
E fique à vontade aí, tá? Ele vai apresentar em inglês, que ele se sente melhor, porque já faz 15 anos que ele está nos Estados Unidos. Então, ele se sente mais à vontade falando em inglês. Mas, se vocês tiverem dúvida, também pode apresentar em português, que você entende, né, Bruno?
Claro.
Então...
Obrigado.
Muito obrigada.
Está a funcionar?
Agradeço.
Conseguem?
Ok.
Não é preciso? Ok.
Pode falar.
Obrigado pelo convite, pela hospitalidade. Peço desculpa, realmente, nas coisas mais técnicas, prefiro...
Só te falar uma coisa da apresentação. Gente, não posso deixar de falar que ele recebeu o prêmio de cientista júnior da Sociedade de Sistemas Complexos, em 2015. Eu não podia deixar de falar exatamente pela produção científica dele na área de redes complexas, de sistemas complexos. Desculpa, Bruno, mas é uma informação importante aqui para a gente.
Mas como estava a dizer, o português falo facilmente, sou português, sou de Portugal. Em termos técnicos, como sempre ensinei em inglês, prefiro falar em inglês, é mais simples. Se precisarem fazer perguntas em português, também não há qualquer problema. Ou se precisarem que eu explique alguma coisa em português, farei os possíveis. Mudando então para inglês. So today I'm going to talk to you a little bit about, and this will be a very, very practical thing, so I'll give you code examples and code. You can get everything from GitHub over there. Both the slides that I'm showing you here and all the code snippets that I'll show you. I'll show you also how the code works. I'll explain step by step. You'll see it, actually, if I can get internet working. You can actually see the code working and downloading data directly from the internet and doing all of those things, but I'll fix that in a second. So let's get started. All the code I'll show you today will work in Python 3.5. That's the version I'm using. So my recommendation would be that you use Anaconda, install Anaconda, because it already comes with all the packages and all the information that you need, everything. Most of the things are already there. Some not necessarily, but most of them are. I'll also give you a little bit of an overview of how QGIS works. So this is a tool to handle shape files and raster files for geographical information systems. So anything that has, in a sense, in a very simplified manner, anything that deals with latitudes and longitudes and projections on maps, how to generate maps. So to get started, I'll talk to you a little bit about complex networks. What are networks? So mathematically, these are called graphs. You might have heard of them. The point of networks is that they tend to be everywhere, and they tend to be everywhere both in nature and in technology. Right? So here we have several examples. This is the backbone of the internet. This is a trophical network of plankton in a lake. So here each node is a little plankton animal that eats another animal, and whenever something eats something else, there is a line connecting them. This is a protein interaction network, so each node is a protein. Links imply that this protein interacts or interferes with that other protein. This is a real neural network, so these are actual neurons and connections between neurons. This is the power grid of the US, so each major power station and each connection between power stations is represented here. And of course, the most interesting network of all is the social network, right? The network that connects people, where each node is a person, and an edge represents some type of connection between people, some type of relationship. So just a few definitions to begin. Oh, this is also another interesting one. So this is actually a Twitter network. So here each node is a Twitter user. And these are users that were in around 2010, they were discussing politics in the US. Right? So here you have actually two types of links. So you have orange links and you have blue links. Orange links means one user mentions another user. So they tag the user in a post if you want, if you're more used to thinking in terms of Facebook. While the blue link means that they retweet each other, so they reshare the post of each other. And what you can see is when you throw this into a layout algorithm, that you immediately get these two very well-defined clusters, right? And this is actually not terribly surprising when you look at it and when you start thinking about it a bit more carefully, and when you start actually seeing what these people are talking about, you'll notice that one blob actually corresponds basically to Democrats and one blob corresponds to Republicans, right? And from here you see already that sometimes, even though you can have multiple edges between the same pair of nodes, edges can represent different type of relationships and different type of connections, right? So in fact, the blue links, the retweet links, actually mean to some degree under agreement. So I agree with you, so I'm resharing what you're posting because I liked it. While mentions are more ambiguous, right? They can mean you're mentioning someone or you're tagging someone. You can do it to compliment them, or you can do it to insult them. Right? It's not strictly positive. And this is why you have these two connections. So the retweets somehow represent within group agreement, while the mentions represent communication within the group or across groups. To clarify, usually whenever I talk about networks in Twitter, I always define the direction of the links, so the direction of the little arrows, in the direction of information flow. Right? So this means that if I retweet you, that means that I saw information that you posted, and I received it and I reshared it. So that means there is a link coming from you to me. While if I mention you, I'm tagging you. You get notified that I tagged you, so I'm sending you information, so the link goes from me to you. Right? That's what I represent here. Of course, you can also define the degree of the node, how many connections it has, both in degree, how many connections it has coming in, and out degree, how many connections it has outgoing. You can define the strength of each node, so how wide the strength of each edge, so how wide the edge is, how big the highway, if you want. The weight of the edge. The strength of the node is basically the equivalent of the degree, but for the strength, so the sum over all the strengths. And these, of course, are both represented both for in degree and out degree, for in connections and out connections. So this is more... I know... Okay. Is it better this way? Yeah, good. So this is like graph theory in 30 seconds or less. So let's see how we actually do this in practice. So in Python, one of the main packages for handling networks is called Network X. This is also included in Anaconda, so if you have Anaconda, you already have it installed. This is actually developed originally at Los Alamos National Lab, so it was developed by physicists, for physicists, to work specifically on this type of problem, so it's very well done. It has a very simple Python interface. In fact, it's actually completely implemented in Python, so it's very easy to handle. Since it's all implemented in Python, it also means that the nodes and the edges can basically be any type of Python object you want. Anything that you can put inside the dictionary, you can put in the graph. It supports 4 different types of graphs: undirected graphs, directed graphs. Actually, that should be directed, not undirected. multi-graphs, so graphs with multiple edges between the same nodes, and they can be both directed and undirected as well. So the interface is the same, so you can just define the object for whatever type of you want, and then all the functions should work more or less the same. The nodes can be any type of Python object. And how do you do this? So you can add a node. If you have a graph, you just do add node with a node ID, and this will create a new node with that ID, right? So that label representing the node. You can give it a list of nodes. Right? So instead of giving it a single one, just give it a list or an array with several. You can do the same thing for edges. So you add edge from node I to node J. Depending on the graph, of course, this will be either a directed edge from I directly to J or an undirected edge. Or you can give it a list of tuples where each tuple represents an edge. And again, the edges will be interpreted depending on the type of graph that you have, the type of object that you have. You can remove a node either individually or from a list. Same thing for edges. But in general, removing tends to be a bit more expensive. So if you want to avoid removing things from the graph, if you just do the graph object.nodes, this will give you a list of all the nodes. So basically a list of all the labels that represent the nodes. .edges will give you the list of all the edges. .degree will give you a dictionary. And so the key of the dictionary is the label of the node, and the value is the degree of the node. And this, of course, can be in degree or out degree in the case of directed graphs. There's also many. I won't list them all, just mention a few functions that actually let you measure directly properties of the graph. So in this case, is connected will tell you if the graph is connected or not. Are all the nodes connected, or do you have isolated pieces? In the case of directed graphs, the node can be strongly connected or weakly connected. This means that, so strongly connected means you can reach any node from any other node following the edges along the direction of the edge. And weakly connected means you can only reach every other node if you ignore the directions on the edges, right? If you treat the graph as being undirected. And the connected components will basically give you a list of the nodes that belong to each component. Right? So this would be a list of lists. So here is our first code example. So just to clarify, whenever I show you code, the example will be more or less self-contained. So a piece of code that does exactly one thing. The name of the file I'm showing you here will always be over there on the right-hand corner. And if I'm mentioning some type of documentation or some type of library that's more unusual, I'll put the link to the documentation up there so that it's always more or less organized in the same way. You can always understand it more or less the same way. So here is a very simple example where I'm basically generating a Bayer-Albert graph. So this is probably one of the simplest graphs that will give you a scale-free network. So it's just preferential attachment. It's doing it in a bit in a funny way. So I'm generating all the nodes I want. So here my labels, my node IDs will just be integers between 0 and n-1. And I'm adding them all at once. I'm generating the edges. So this represents a triangle. So an edge from 0 to 1, from 1 to 2, and 2 to 0. So this is actually a flattened representation. So it's not the list of tuples that NetworkX is expecting. The reason I'm doing this way is because it's very easy then to implement preferential attachment if you represent it this way. This way, if I want to connect to a node preferential to its degree, I just have to choose one position at random in this array. And that's always preferential to the degree of the node by construction. So at each step, I do this. And so basically, I'm adding n nodes and n edges. So at each time step, I'm adding one node that has exactly one edge outgoing. Although in this case, it's undirected. So I'm choosing to connect to one of these little stubs at random. And I'm adding it to the list, both the new node that I'm adding now and the edge that it comes from. And then I'm basically reshuffling, turning this flattened list into that list of tuples, and then just feeding it to NetworkX to generate the graph. And this will just return the graph. Right? So this is a little bit simple. If I'm going too fast, let me know. Don't be shy. Now, and here is basically the rest of the program. So basically here I create the network. The network is the function I just showed you before. I'm hiding it over here. I'm getting the degree of the network. I'm calculating the degree distribution. So this gives me the dictionary of where for each node, it gives me the degree. For each node ID, it gives me the degree. I'm basically counting how many times each value is appearing inside this dictionary, and then I'm just putting that into an array. And I'm plotting it in a log-log distribution and saving it as a figure. And at the end, I'm just printing how many nodes and how many edges I have. So you can actually see this running very quickly. Let's make this big. See if you can actually see that. So this will take just a few seconds to run, and you will print out basically a few statistics, and you'll generate the plot of the degree distribution. And you'll see the degree distribution. So you'll see, tells you it has 1 million nodes, 1 million edges, it's completely connected, it's undirected. Right? And if you investigate here, you can see that it also generated the image for the degree distribution, which you can see, which of course opened in the wrong screen, as always. Which is this, but you can see it better from here. And you can see even by eye that this has a slope of -3, right? So it goes down 6 decades here, goes around 2 decades there, so you get a slope of 3. And this is, you can prove very easily mathematically that this process should give you a power law degree distribution with slope -3. So this was just a way of introducing more or less network X, because it's something that's going to be very useful in many applications later on. And also, most of the things I'm going to do later will somehow use this idea of network and how you navigate the network, how you jump from one node to the other following edges and that type of thing. In particular, one concept that's particularly interesting when you're doing data mining is sampling, right? How do you get information about the graph, right? If I want to get information about the structure of the Twitter network, how would I do it, right? One typical way of doing it is using what's called snowball sampling. So what this means is you start with a node, you find all the friends of that node, then you find the friends of the friends, the friends of the friends of the friends, etc. Right? So it kind of grows like a snowball. So this is very common in both social science and computer science, so you might even have heard of it already. Basically, you start with a single seed node or even several seed nodes, depending on what you want. You get the friends list, so all the edges that are outgoing from that node. And then for each outgoing edge, you basically follow it and you repeat the process. Of course, you have to be a little bit smart and keep track of the nodes you've seen before, so you don't go around in circles. So you keep a little bit of a list of a set of all the seed nodes, of the nodes that are on the boundary that you're going to visit next. This has, which can be an advantage or a disadvantage, the property that it generates a connected component always. So starting from one node, you're always going, you're restricted to being inside the same component, right? If there is no way, if you have two pieces of the graph that are disconnected, that have no edge in between, and you start with the seed in one of them, you'll never reach the other one, right? And this is why sometimes you have to start with several seeds, either chosen very carefully or chosen at random, hoping that they will cover all the possible components in the graph. The problem with this, of course, is it will also generate, if every time you need to get the friends of a node, you have to make an API call or several API calls, this will quickly generate, and we'll see in a second how to actually run these API calls, generate many API calls, which can cause you problems in terms of limitations, right? And traffic generated amount of information, etc. So in code, this is what it looks like. So we have two sets. One is the set of nodes that have already been seen. This other set that I'm calling Q is basically the set of the nodes I'm visiting next, right, that I haven't seen yet, but are in the boundary, in my boundary. I'm initializing the Q as being the seed node. So first, all I have on my list of nodes to visit is the first node. Makes sense. And I'm keeping this Q2 just as a as a way of making sure I'm not adding nodes twice. Does that make sense? So, and then I just go around. So for how many steps from the seed do I want to go? So how many layers? And then for each layer, as long as I have nodes in the queue, I get one node from the queue. I add it to the list of seen nodes, so I'm moving to that node in a sense. I'm asking that node, give me all of your neighbors, right? All the nodes that you are connected to. I'm putting, and for each node in that list of neighbors, I'm checking if I've seen them already. If I hadn't, I put them in this Q2, and then at the end I just update Q. The reason to keep Q2 there is basically as a way, if I want to do something special with this boundary as it expands, so I can keep track of it. So it's just a convenience. So this is another small example. So this is what it's doing here is I'm generating a graph using one of the functions of network X. Here, in this case, it would be a Watt-Strogatz network, which is basically a loop with some nearest neighbor connections in a very simplified way. In this case, each node has degree 4, so it's connected to 2 nodes on each side of the loop. And here I'm asking for a snowball sample of depth 0. So it just means like once starting at node 0 and depth 3, because that's the default value I set there, and that most will give me 1,000 nodes. So you can already see that if I have a ring of numbers, each numbers that are sequential, 0, 1, 2, 3, all the way to 9,999. If I go 3 steps in each direction, I'll get 0, 1, 2, 3, 4, 5, and 9,999, right? So this is what our code should give us. Yep, here we go. So so you can see it works very fast, and it gives you exactly what you expect. Right? So it gives you all the neighbors in both directions. So of course I chose this topology of the graph so that it's something that you can check mentally in a very simple way that it's working and doing what it's supposed to be doing. So this is just a introduction to the networks thing. Now, how do you actually use this in practice to actually get data and to connect to data, right? So the first thing you have to do if you want to operate and integrate with some type of online service is you have to authenticate yourself, right? So somehow you have to log into the system. Like the same thing you go on Twitter or Facebook, they ask you for your login and your password. You have to give this somehow in an automated way to the system. There you go. There are many different types of authenticate methodologies. People develop this in different ways over the years. Of course, many things are only accessible after you log in, either for privacy reasons or commercial reasons or whatever. There's basically 3 main ways of doing this. Basic auth is very simple. You just send your login and your password in plain text to the server, and the server lets you in. Oauth 1 was developed by a consortium of industry leaders. This is actually an interesting story. Oauth actually started originally developed by Twitter because they wanted to figure out a way to give access to third-party applications to access your data as if it was you, without you having to give these services your password explicitly. And Oauth 2 is basically an improvement of Oauth 1, and we'll cover them in a second. That has some added functions, and it's used by other services, in particular things like Foursquare, for example, and even some type of Google Maps APIs also use Oauth 2. And OpenID, which is basically the grandfather of Oauth. And Oauth, in a sense, was developed to address some of the limitations of OpenID, but we won't really cover it too much. So, basic auth. So as I said, whenever there's documentation, you can see the link over there. So this is the mother of all authentication protocols, in the sense that it was the first one. It's the most simple one. It's the most basic one. It's insecure, but it's very easy to use. And pretty much any type of networking tool will accept this. In particular, in requests. Requests is basically one of it's not really a standard part of standard library, but it's almost standard way in Python of communicating with online services as a way of creating connections and establishing connections. So you can, and basically in the request, the way you ask for a web page, like if you go on your browser and you type the URL in the browser bar, here the only thing you have to do is request.get the URL, and it's the same thing. So it connects to the server and it shows you back what the server sends back, the page. So if you want to do this with basic OAuth, so you just have to give it a tuple with your username and your password. Right? And this will open the given URL and authenticate it with the username and the password. Oh, yeah, that's hiding there. So you can see it's basically the same thing. This is actually, so this URL I'm using here, this is actually a service that exists specifically for people to test their basic auth implementation. So the way it works is you say you want to use basic auth and you want to use this username and this password, and then you try to access this URL using that username and that password, and if the two match, it will just say correct. Right? So here you can also see a very, very small I don't have, if I had more time, I would give you a proper tutorial on requests, but here you get an idea of how it works. So you just you request the URL, you get the URL using this OAuth credentials, or these basic auth credentials. One of the fields of the request it returns is the status code, so it tells you if the connection was successful or not. So if the connection was not 200, then it says it's not successful. You can also tell you what is the content type, so what is the type of the reply that the server gave. In this case, the request is actually a JSON, so I'm telling you, okay, interpret this as being a JSON object. And JSON is, in a very simplified way, is just a dictionary in Python terms. And so it parses that dictionary, returns my dictionary, and then I check inside that response, there is a field called authenticated that is either true or false, whether you gave it the right username and password or not. So if you run this, oh, and just to clarify, in this directory, all I have is basically the code I put it in the GitHub repository that you can download. So everything you see me doing here, you can do on your own later on, if you like, or you can follow along as you wish. Oops. Sorry, I was complaining about the internet on the other screen, so I was taking so because it's actually very fast. See. It just says authentication successful because it connected, obtained the response, checked the response said it was successful, so it printed that it was correct. Now, for more serious things, OAuth. So OAuth is defined, so that's the official documentation and how it's implemented if you're very curious. It is officially defined as an open protocol to allow secure authorization in a simple and standard method from web, mobile, and desktop applications. Right? So this is a way for you to give permission to applications to use your credentials in a way that you control completely. So the idea is to allow a safe way to share privileges without divulging private credentials. So you can give some random application permission to post on your Twitter account without you having to physically give it, this application, your express login and express password. Right? This is particularly useful if you tend to use the same password in multiple services, all those things. And also you can revoke the privileges, so you can go on Twitter and say, I no longer want to access for this application to be able to use my account, and remove it unilaterally, right? So you can just do it whenever you want without that implying that you would have to change your password, for example. It also means that you can change your password without changing the permissions that you give. So basically the way it works is a little bit complex, but this is how it works. So this is so here TweetPic is basically it's an old service now that basically posts photos, that can post photos to your Twitter account. Right? And the way it works is you go to TweetPic and you say, okay, I want to log in using my Twitter credentials. TweetPic talks to Twitter and says, look, I have a guy who wants to log in to me using your credentials. Twitter then talks directly to you and say, look, there's this application who says you want to log in to them using our credentials. Is that okay? If you say it's okay, you send the response back Twitter and say that's okay. Twitter says, okay, this guy is who he says he is. TweetPic says okay, and then it gives you permission, right? So you go around this loop twice. So this is called very, very commonly the Oauth Dance, right? You're dancing around back and forth. But after you do all of this, basically, this application can do whatever it wants with your Twitter account as if it was yourself, as if you were doing it yourself. Right? So after this Oauth Dance is concluded, basically the client application now basically has two sets of keys. Right? It has one set of keys that identify itself, identify the application, that says, okay, I am TweetPic, and here is my password. Yes. This is called the API key and the API secret. And there is another one that identifies you as the user. That's called the token and the token secret. And this is more or less equivalent to your login and your password, but they're generated automatically. You can revoke access at any time. So you can just go to Twitter and say, I no longer want to use TweetPic to have access, so you can remove it. Oauth 2 works more or less the same way. So here's represented in a different way. So you say, can I get access? It connects, it's asking you to identify yourself, connects to Google, so it does the dance in a slightly different version, but it works the same way. Here, the advantage of this, and the advantage of Oauth 2 is that it allows you to generate a single token and use just that token as to grant access. And it also allows that the tokens that are generated, for instance, are valid only for a specific amount of time, are valid only for a specific service, so it gives you a lot more fine-grained control. This is the latest version, but the two exist in parallel. Twitter uses Oauth 1, Foursquare, for example, uses Oauth 2, Instagram, I think, uses Oauth 2 as well. So it has a similar dance, allows for bearer tokens. So this is basically a master key that allows anyone who has it to have access directly without any restrictions. Access tokens are provided along with the request, and tokens can expire automatically, right? So that you can just say, I want this token to be valid only until tomorrow, and then after tomorrow, the service will no longer accept that token. And we actually won't do this because I don't have time. This is only one day and not several days. Now, Twitter, you might have heard of it. This is an old idea. And the idea is and this is actually a machine that existed in London in the 30s at some point. And the idea was very simple. You put a little coin in the slot, you get a piece of paper, you write a message in this piece of paper, you put the paper in the machine, and the machine will show this message for a certain amount of time. Right? So this was a simple way for people to make announcements. Like if you're wanting to hire someone, you could go there to the machine, and they will show this piece of paper, this announcement, for a certain amount of time. I don't remember how long exactly. And so this is the basic idea of Twitter. Of course, over the years, it got a bit prettier. Now it has birds. But the idea is the same. Right? So this is what a tweet looks like. You have a small message that you can post. This message is limited for historical reasons to 140 characters. So it's very small. So it's smaller than an SMS. But despite being so small, people become very creative about how they use them and find smart ways to squeeze as much information as they can into this small piece of information. So in particular, they created the concept of hashtags. So these are topic markers. They mark more or less what is the subject of the tweet. They started including URLs that point to further information somewhere else. You also have, of course, associated with the tweet, the author of the tweet. You have how many people retweeted it, who were the people who retweeted it, when the tweet was posted, where it was posted from, so it even has geographical information, etc. So despite the fact that the tweet is limited itself only to 140 characters, the metadata that it includes, it can be 3,000 or 4,000 characters, so it's a very large thing. In particular, it has many different fields. So again, this is a JSON object, so it's a dictionary in very simplified terms. This dictionary has many fields. Particularly interesting is the user field that has a different dictionary inside that has many properties of the user profile and the user account. It tells you, for example, what is the user ID. It tells you how many followers the user has, how many friends, how many tweets it has posted. if it has geolocation enabled or not, what is the screen name, what is the language of the profile of the user, etc. Of course, the tweet also includes the text, so this is what you're actually posting, what is the actual message that you're posting. Here is a check-in in a feira somewhere in Brazil. Source is the application that was used to post this message. Like we saw with Oauth 1, you can give permission to other applications to post things in your account. This is what they look like after they do it. Entities is a list of different things. It has symbols, user mentions, hashtags, and URLs. So this is basically a service that Twitter does for you. It pre-processes the tweet and gives you already a lot of information about what's in the tweet. So in particular, it tells if it's a URL, it tells you what is the URL that is showing, what is the expanded URL, what it's pointing to, where it is in the text. This is from character 70 to character 91, and what is the actual URL, it will show up there. If it will also do something similar for hashtags, so where the hashtag is, where it is, etc. User mentions what users are mentioned and where in the text of the tweet. So if you want to clean the text of the tweet of removing all of these things, it's very easy. And then, of course, it also has the geofield. The geofield is basically, if you're posting it from your cell phone has a GPS receiver in it, so it has a latitude and longitude. It will show up there. It will be inside the geofield. Which, yes. Yes. Yeah. So the geofield will just give you latitude and longitude. I thought it was showing here for some reason an example, but it's not. Now, before you can do this and you can actually talk to the API, you have to actually register an application. Right? So you have to create your own fake application. So you have to go to the apps.twitter.com, say I want to create a new application. You fill out a little form, which is not terribly tricky. And this creates the application and basically gives you the API key and the API secret, right? So this, like I said, in the discussion of Oauth 1, this is what identifies your application, right? So this is step 1. Step 2 then is you have to give permission to this application to use your account, right? So if this was a commercial application and you wanted to give it to the public, then you would point the user to some URL, and then the URL would do basically the Auauth Dance that we saw before. Here, since it's your own account, and usually people, when they generate an application, they want to use it with their account for testing purposes, so this makes it easier. You just say create an access tokens over there, and that generates you the access token and the token secret. Right? And after you do this process, basically you have the 4 pieces of information that you need to start talking with the Twitter API directly. Right? You have the API key, the API secret, the token, and the token secret. My suggestion always is that you put all of these 4 pieces of information inside the dictionary, hiding somewhere, which I will show you here. Yes. And then, actually, I'll show you that in a second. Now, you can, of course, interact directly with the Twitter API if you want. There are URLs. You can connect to them directly. There's also Python modules that make your life easier. In particular, I'm going to use something called the Twitter module, which is very, very simple. I like Twitter module in particular because first, it makes it easy for you to generate the Oauth, to manage the Oauth connection, which is good. And so I was saying, keep all the credentials, so the API key, secret, token, and token secret inside the dictionary. And you parameterize basically the API calls with calls to this dictionary. This way, this makes it very easy for you to handle multiple sets of credentials, because then you just have to change one line of code without changing everything. So you just do Twitter auth with your Oauth token. This will give you a Twitter object. One other reason why I like this specific module is that the method, so the way the module is structured, matches exactly the official API. And I'll show you this in a second. And there's basically 4 types of objects that you're interested in. You have tweets, you have users, you have entities, and you have places. There we go. And yeah, for every type of objects. So here I'm putting all my API token, secret, key, and secret inside a file called Twitter account, inside a dictionary called account, and I'm calling this specific account, I'm calling it social. So then if I want to basically rerun the same code with a different account, I'll just have to change this line, and the code would still work, and it'll do the same thing. It will just identify itself using different credentials, right? So this makes your life much easier. So, yes. So this is how you authenticate. So most of the code you will see next, that user's Twitter, will start with these 3 or 4 lines of code, basically to generate an object. So what I'm calling here the Twitter API is basically an object that allows me to interact directly with Twitter, right, programmatically. So let's try to do something useful. So how would you search for tweets, right? You want to search for what's happening now, for example. So you do Twitter API.search.tweets, right? And here already you can see, so that's the official documentation in the Twitter website. So the docs API 1.1 get, and then you see search/tweets, right? So .search.tweets. So the method and the documentation match one-to-one, so it's very easy. So even if you don't know what the method is, if you find it in the Twitter documentation, you can map it immediately. If you're looking at somebody else's code and you see a call that you don't recognize, you can immediately find the documentation. Right? So it makes it very easy. Query is the thing you're searching for, is the string or the words or whatever you're searching for, and count is basically how many results you want. Here you're limited to 200. And this what this returns, if you do this call, it will return you a dictionary. They'll have a list of statuses, and statuses is what Twitter internally calls tweets, and search metadata. And the search metadata is basically this. It's this little dictionary here. Tells you how long this operation took, how many results it returned, what is the maximum ID of the tweet that was returned, how you can get the next page of results, what was the query. So here the query, I was searching for soccer. What is the refresh URL? So if you want to get refresh, like if you were pressing refresh on the browser to get an updated search, this is the string you'll get. And since ID, so basically what was when were you searching for? If you were searching for the most recent ones, or if you wanted to search back from some specific tweet. The search inside the search results, you get the search metadata field, and then it has the next result. So it is this string here. Basically tells you how to get the next page of results. And so it tells you what the information is. And you can parse it basically to extract the max ID. To extract the max ID so that then you can feed it and say, okay, I want to search results, but only older than this tweet. Right? So here is an example. Here I'm not showing, just for simplicity, because I don't have space, I'm not showing those first few lines in the beginning where I do the authentication. I'm going to query for Instagram. I'm going to get 200 results at each step. This is how I do the search. So a Twitter API.search.tweets with this query, with this many results. This is how I get my search results. They're hiding inside this list here. And then I keep asking for more results. I look at how to get the next page of results. I parse to extract the max ID. Oops. Oh, sorry, there was a pop-up here. And then I ask for the next page of results. And here I'm just printing, every now and then I'm printing how many results I already have and printing the text of the tweet so that you see something. So let's see this running in real time. Search. Hopefully the world won't explode. This worked fine yesterday, so it should work fine now. Yeah, so it looks like there's some problem with the connection, so it's not resolving the DNS server for some reason, which is weird. Let me try disconnecting the internet and reconnecting, see if that helps. Otherwise, you'll just have to believe me that this actually works. And now it's actually refusing to connect to the internet completely. So no demos for you today, sorry. So, I promise you it worked yesterday in the hotel. So that was to search tweets. This is how you stream tweets in real time, right? So searching, you can think of it as saying, okay, give me the results from here going back, and here it's complaining again of the network, that's okay. From now going back, so recent past, while streaming is from now going forward, right? Give me new results as they are arriving, as they are coming. So you can filter this stream based on different things. In particular, so instead of using a Twitter object, you generate a Twitter stream object, but it's the same way, the same idea. You say, I want to filter on a given query. So you can think of this as being almost as if you had access to the entire stream of tweets as they're arriving. Stop trying to connect. As they're arriving in real time from all over the world, and then you're just choosing the ones you want from that, right? So you say, I want only the tweets that match this query. And this would return a generator that basically you can put in a loop and get the results one by one, tack, 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 tack. So this is what the code looks like. So now I'm showing you everything because the code is a little bit shorter. Here I'll search for Justin Bieber, because there's always people talking about Bieber, so it's a good demonstration query string, and basically we just print out the tweet of the text. All right, the text of the tweet. And here it's still refusing to connect, so I think I'll just turn off the internet and give up on that. So you just have to believe me that this actually works. Actually, in a little bit when I start talking more about how to get to geolocate the data, yes? So the stream, it connects once, and it stays connected, right? It will just keep, so you can put in a for loop, and it will just give you results as they become available. In general, Twitter will block you if you make too many requests too quickly. If I remember, they keep changing the number, but if I remember correctly, you basically get one request per second, more or less. And it depends on what type of request it is. They count different request types are subject to different constraints. So you might be able to do more things or less things depending on exactly what you're doing. But here, as you can see, it basically connects once and gives you the generator, and then you just keep asking for more results of the generator, and this you can do as fast as it will give you the results as it gets them. Oh, and like I was saying, when we get to talking about geolocation, in the repository, I actually have a file with tweets that we're going to use so that we're not dependent on the internet to actually observe something. You can also get the user profile. So this is information about the user by looking up the user using a user ID or the screen name. User IDs are always numerical. Screen name are the username that you use, so like Big Goncalves over here. You can give it a list of user IDs or a list of usernames. The list should be comma separated and provided as a string. So here is an example. So again, this is just the authentication. I'm going to ask for the user object for these two users, Diunito and Giarufo. and say, look up, give me this, and these are screen names. If these were user IDs, I would put user IDs here. So user ID equals that. And here I'm just, for each user, I would just printing how many followers it has. So it's just a very simple example. Yes. Não é culpa minha. Não, não faz mal, não faz mal. You just have to believe that it works. And maybe after the coffee break, it will start working again, we'll see. It's okay. Now, another thing, like I was saying, all of this you can think of Twitter as being a social network. So each node is a user. You have connections between users if they follow each other. There's two types of connections. You can be a friend or you can be a follower. So if your followers are the people that follow you. Your friends are the people that you follow. So like I was saying in the beginning with Network X, you have the incoming connections and the outgoing connections, right? So your friends are your incoming connections, are the people you see information coming from. Your followers are the people you send information to, so your outgoing edges. You can get from friends IDs and followers IDs, for each call, you can get up to 5,000 friends or followers. Of course, if the user has more, you have to do multiple requests. This will give you a dictionary containing multiple fields. The IDs is where all the IDs of the users are, of the followers or the friends. So they're all hiding in there. And next cursor basically tells you how to ask for the next page of results. So if you have a user that has many followers, you'll get them in pages of 5,000 followers at a piece, which sounds like a lot. But if you think that, for instance, I think it was Kylie Minogue a few weeks ago just passed 100 million followers, you can see that this can take a long time. So friends.id is screen name, cursor, and then you just put the value from that field in the dictionary, and it will just give you the next page of results. And cursor 0 means no more results. So when it tells you the next cursor is 0, then it says you're done. So, and this is what it looks like. So again, this is just the authentication. I'm going to search for the followers of Stephen Wolfram, just randomly. So I'm starting with cursor -1, and while the cursor is not 0, I keep asking for more, right? And the cursor is what I'm getting, and here I'm adding the new results to the list of followers I have, and I'm updating the cursor, and as long as the cursor is not 0, it will keep going. And then at the end, I'm just printing how many followers I found. And if I remember correctly, he has about 25,000 followers. So this will take a couple of seconds to do this a few times, and then it will work. And then you will print out how many it found. Yeah, I can show you that. No, that's okay. You can also ask for the user timeline. So the timeline is basically everything that the user has posted, right? The entire history of that user. Of course, there's a few important options when you ask for the timelines. If you want to include the retweets or not, so if you want the tweets that user retweeted or not, or just the tweets that user posted directly. And this, of course, also includes tweets posted in the user account by other applications, not directly the user typing in this by hand. And here, trim user equals true if you want to not include the user information from each tweet. Like we saw in the beginning, each tweet has a field that says user, that has information about the user. Since you're getting many tweets from the same user, you're just getting this field repeated over and over and over again. So you can say trim user equals true, and then it won't include this, and you'll make the connection faster because you're downloading less data, basically. And max ID is basically only tweets with an ID before this. So you say, it's a bit of feedback, I think. And you'll get only tweets with an ID lower than this. It means only tweets that are older than this tweet, instead if you don't want all of them. This will give you at most 200 tweets in each call. It will also give you at most 3,200 tweets. For some mystical reason that is never really explained, this number of 3,200 is more or less is on average. It's not exact. So sometimes you'll see 3,220, sometimes you'll see 3,180, or somewhere in between. But on average, it's around 3,200. It's not I don't know why it varies or how it varies, but it does. So here is the code. So again, authentication. I'm going to get the history of Barack Obama. I want 200 tweets. I'm trimming the user. I'm including retweets. I'm asking for the user timeline and just giving, here, this is just one of the Python ways of feeding a bunch of arguments to a function, is you put them in a dictionary, and then you just unpack the dictionary in the function call, so that makes the code a little bit more compact. And this gives me tweets, and then as long as I have new tweets, I keep asking for more, and then I'm just printing how many tweets I get. And if I remember correctly, last time I did this, I got like 3,218 tweets. So it's never exactly 3,200. You can also, because you have the entire history of what the user posted, in a sense you also have the entire history of the user interactions. Right? You can see who the user mentioned, you can see who the user retweeted. And this is basically a way to extract that information. So this is an addendum. So the previous file I showed you ends here. And this is how, from those tweets, you would extract basically the interaction network. Right? So for tweeting tweet, if it's a retweet, you're printing the user and the user it's retweeted. Actually, this should be the other way around to follow the convention I said of the information diffusion. And then if it's a reply, then you say the reply and then the user. You can see, so that you can see how the information is flowing in both cases. Okay, I still have time before the break. So we're doing well. Yeah, fine. The streaming API gives you, like I said already, you said you can stream tweets based on specific queries. You can also stream tweets based on locations, right? So this is particularly useful. So the streaming API provides real-time data subject to filters. Already saw this. You have to use the Twitter stream object. You can match a query in real time. This will give you the generator. But instead of doing the track equals Q, you can say locations equals a list. And this is a list of coordinates for a bounding box. And we'll see in a second what a bounding box actually is, but it's basically a rectangle. And you're giving it the coordinates of the lower left corner and the top right corner. Right? So you're defining what is the rectangle, and it's giving you tweets inside this rectangle. Now, one thing that is important to remember, so this is a comma-separated pair of longitude and latitude values. One thing that's important to remember, is the order in which these appear. Different services will have different conventions. Some will use latitude, longitude. Some will use longitude, latitude, just to be different. The reason to use longitude, latitude is because this is, you think in Cartesian terms, this is X and Y, while latitude, longitude is the historical most correct one. So if you give BB equals this, it will give you tweets from the entire world. If you say give this, it will give you basically New York City, more or less centered around Manhattan. And here is how you actually use this. So again, authentication, you're getting a Twitter stream. This is the query I'm using, so I'm getting things for New York City. I'm asking for results. I'm dumping all the results basically into a file. So for each tweet, I just print it out. I'm just printing out the tweet ID so you can see how it's running, and then I'm printing the tweet into the file. That's it. And I'm stopping after 10,000. So I can't show you this running in real time, but because with demonstrations, internet problems are not unusual, I'm actually already including a file in the thing, so you get basically a bunch of tweets, and this is what the tweet looks like. So each line is a tweet, and you can parse each line, parse it to get the dictionary, and then you have all the information there. And you can check that this actually has 10,000 exactly 10,000 tweets from around November 2015 or so, which is when I first generated this file. Okay, so right now, you're probably bored of listening to me already, but it's only been 1 hour, so you have 3 more hours to go. But right now, what I've shown you is basically how you can connect to Twitter and get data from Twitter. What I'm going to show you in a second, from now on, is more different things that you can do with this data and different ways of analyzing this data. Of course, there are many different services that can give you geolocated data. I don't have enough time, or I could give you many other examples: Wikipedia, Foursquare, Instagram, GitHub even, Google Maps, etc. But after you have geolocated data, after you have latitude and longitude, then you need to know how to analyze it and how to process it. And that's what I'm going to focus more in a second. Right? But first, let's look at language detection. Right? As I showed you in the beginning, you get the text of the tweet. From the text of the tweet, you can know what is the language it's written in. Right? One way of doing that, of course, is you need to do some type of language detection algorithm. And there are many. One of my favorites is the one used by Google, right? Google Chrome. So if you use Google Chrome, if you go to a random web page written in some random language, this is Catalan, you'll get a little bar on top that says, oh, look, this thing is written in Catalan and you don't understand Catalan. Do you want me to translate this for you? Right? Let me translate this to English. And if you press the magic translate button, it will magically translate it. Right? And this is great. Right? So you can see that inside this little bar, there's a lot of know-how and a lot of technology hiding in there. But fortunately, at some point, Google decided that they should publish an open source version of Chrome. They called it Chromium. They made it blue. And some crazy guy basically dug through the code and extracted the library that does the language detection. Right? So you give it, and basically what you have here, you can install it. It's a bit tricky to install, but you can install it. What you get is a simple Python library where you give it a piece of text and it returns what the language it's written in. It's as simple as that. And it tells you even more. It tells you how sure that is the correct language. So it tells you a measure of the likelihood, or what is the probability that is the correct language. So it can tell you, for example, I give it a piece of text and it can say, I'm 95% sure this is English, maybe 3% sure it's Spanish, and 2% sure it's Portuguese. And which means you can put a threshold and say how sure you want to be, and then use only that. This, because it's Google, covers languages basically from around the world. It's about 70 or so of them. This list is from February 2016, so it's more or less when the last version came out. So it should be more or less correct. This is the CLD, how it's called. It's the module. You can install it from there. This is a C package that has C++ bindings and Python bindings, so you can call it from C++ or from Python. It's particularly messy to install because it was done in a bit of a hacky way, but after you install it, it's very fast. And basically, you just do cld.detect, you give it a text, and it gives you the list of all the languages. Simple as that. It's very conservative, so if it's not sure, it will just say, I don't know, unknown, which is, for me is a good thing. And version 2, so there's CLD and CLD2. Version 2 is better, so it's an improved version, but it's better and it's optimized for longer pieces of text, like web pages or books or blog posts or whatever. And it can handle even like cases where different parts of the text are written in different languages. Right? So tell this piece is one language, this piece is another language, when you have quotes and that type of thing. I prefer to use the CLD version because it works better with small pieces of text. So this is an example. So here I have a text in Italian and a text in English, and I'm asking what are the language Google think it's in. Actually, what's the name of the code? Language CLD. Oops, all right, because I forgot to install this in Python 3, so just for this example, I'm going to use Python 3.5, because I'm lazy. Here we go. So this one, which is written in Italian, it says it's in Italian, and I'm 100% sure. And this number here is the minus the log likelihood, so it's more or less useless if it only gives one language. Here's another tweet, and it says, okay, this is in English, and again, I'm 100% sure, and that's the likelihood. Actually, before I forget, let's move back to Python 3.5, otherwise I'll forget. And things will stop working afterwards. Now, you can easily see that if you get a large number of geolocated tweets with latitude and longitude, and you run them through language detection, you can start seeing where the languages are used, right? So let's take a look at Brazil. So that's a very dark map of Brazil. Here, you're seeing basically all the tweets I had at some point in Brazil. This, I think, is from a paper from 2013, so it's a little bit out of date, but it's still nice. But then you can say, okay, I have all of these tweets. Now show me only the tweets that are written in Portuguese, example, right? And you find out that there's about 82% of the tweets, of the geolocated tweets are written in Brazil are written in Portuguese. Of course, you can see immediately also, I should mention, you can get all the major cities you can get even major highways and railroads, etc., connecting cities. Then you say, okay, the second most popular language is English. Of course, you tend to find it more in more touristic places like Rio, Sao Paulo, etc. And there's a little bit of Spanish, which again is in the big cities and closer to the borders. And then there's a bunch of other things that I want to mention. Now, another possibility, instead of using CLD, so this was all done with CLD, with the Google Chrome language detector, compact language detector. Another possibility is LangID. So LangID is written entirely in Python. You can install it from there. It supports 97 languages, so this is actually more languages than the Google one. It tends to be less conservative, so it's more likely to give you an answer, even when it's not too sure. So I prefer to use CLD, but depends on what you want. One thing that's interesting about this one is that it gives you the option of getting the results for every language it knows and not just the top 3. So this can be interesting if you want to do comparisons between languages. Instead of doing, so you just do .classify text, and it'll give you what is the most likely language, what is the likelihood. .rank text will give you the list of all the, or I think it's a dictionary, with all the languages and the respective likelihoods, okay? So this is what it looks like. So it's exactly the same code as before. I'm just switching CLD by LangID. That's exactly the same code, and asking to classify it and printing it out. You can also see it takes a little bit longer than CLD because it's doing everything in Python instead of doing it in C. So again, it tells you that this is Italian, it tells you that this is in English, and tells you how sure it is, and what is the likelihood that it's correct. So in the next, before we break, I will give you a little bit of a review of the Google Maps API, which is actually surprisingly useful. So you're all familiar with Google Maps, so this is where we are right now. This is what it looks like when you go on an actual web page. But internally, you can also use the APIs and actually interact with this service directly programmatically. Right? So you have to ask again for the API key and your Oauth client ID. So, and this you can just ask for them. It makes it very simple for you. You just create a general ID, you give it a name, and they'll just give you the credential, the API key and the credentials directly. You can see it's using OAuth 2, like I mentioned. This is the API key, which I'm hiding. And then for each API you want to use, you have to enable it. So you have to say, I want to use this API, but you only need to do that once. So after you do that, you can use them all. So each API has to be enabled for a specific set of credentials. So this, for instance, would be the API if you want to show a map on the web page. Now, as before, we put all the credentials in a little dictionary, hiding in an external file. You can see an example of that file here. The actual file I'm using is Google_accounts.py, the stub is just this one that I'm showing you here. Google gives you dozens of different APIs. The Google Maps Python library, which is very easy to install and very easy to use, lets you interact with a few of the GIS-related ones that makes it very easy. So directions, distance matrices, elevation, geocoding, geolocation, time zones, roads, etc. And places. These for us are particularly interesting, the directions API, distance matrix, geocoding, and places. I think I'm only going to talk about, I have time to talk about the geocoding and the reverse geocoding. So this means going from an address to latitude and longitude, and going from latitude and longitude to an address, right? Because these are the most useful for the type of things we want to do. So the geocoding API, so again, the documentation is over there. This gives you the latitude and longitude from a specific location. So here, because it's using OAuth 2, you only need to give it the API key, so it only needs one value instead of all those four. And then, so this is all you need to do for the authentication. And then it just says, tell me where JFK Airport is. And you'll give you a big dictionary, and inside this dictionary, we'll give you the latitude and longitude. So as the previous APIs, this will give you a JSON object, so it's just a dictionary. Each result gives you detailed information. It tells you what the address is, a bunch of what type of location, what is the place ID, so you can get even more information. Inside the geometry field, geography, I guess, field there is a location. And the viewport is basically, if you were showing this on the map, on the sim, this would be basically the box that you would show with the location in the center. And the type ID, which basically can be used with the places API, which I want to talk to get more information, user reviews, user photos, all sorts of things. This is what the result looks like. So it's a big dictionary. It has address components, so it splits the address in different things. It says it's inside the US, it's inside New York State, it's inside New York City, it's in Queens, and here it is. So it gives you different levels of approximation. You can see, so it's an airport, it's in Queens, inside Queens County, inside New York City, inside New York, inside the US. This is the formatted address, so the official address, geometry, location, and then the latitude and longitude. Location type is approximate, of course, because it's a big thing. It's not an exact place. The viewport is basically the window that you will show. The place ID is the unique ID that identifies this object inside the Google database, if you want. So, and these, of course, are the most interesting ones. You get the location, which is what you want, and the viewport, which might be useful or not, and the place ID. Yeah, I don't have internet, so I can't show you that actually working. Yes? It's back? Let's see if I can do it now. Or if I'll just explode the internet again. You never know. Now it's trying to connect. Okay, it says it's connected. Let's try and show you the one that I didn't show you before, because it wasn't working. Twitter search, yes. Here we go. So these are real-time results of tweets happening right now, basically. And you can see that this basically covers every language. So you have, just from here, you already see Portuguese, you see English, I've seen Russian somewhere, Arabic, Korean, Japanese over there again. So, and now Python, Geocode. There you go, and this gives you the latitude and longitude, because that's what that code was doing. Yeah, so this is just this little piece of code, just printing the geography and the location. And that should be geometry, I guess. So, and reverse geocoding is basically doing the opposite. Given a location, latitude and longitude, it tells you things that are in that location or nearby. Right? So you give it a latitude and longitude. Google has many layers, so it will give you many different results based on different criteria. Right? So it will give you buildings, it will tell you what is the nearest road, it will tell you what is the county, what is the zip code, what is the state, what is the country, etc. Right? So when you do reverse geocoding, this is what the result looks like. And I'm putting this piece of thing in that little JSON file over there. And here I'm geocoding just some random place inside New York. So the address components, it tells you what is the city, what the locality, what is the administrative area, so basically the state, what is the country. The geometry, the location, the place ID, and the type. So it's a locality and it's a political division. And this is how you would do it. So this is asking for the reverse geocode of these coordinates over here after the authentication that we saw before. And basically for each type of result, it's printing the formatted address. So it's basically just telling you what it is. A little bit there. So it gives you a road nearby. It tells you what is the political sublocality, what is the locality, the postcode, the administrative area, the different political divisions, administrative areas, and the country. And this is basically all that you would see if you did the same thing in Google Maps India. Right? You see the road, you see the place, it tells you what it is, and that's the same coordinates I used. So it's basically giving you everything. And just to give you a small visualization of what it's doing, it's basically showing you different areas of approximation, different types, different layers. Right? So, and these tend to be basically overlapping rectangles. So if you run this from that file, this is what you get. You basically get the rectangles that it's showing. So the big rectangle is the country, the other one is the state, the city, the county, and you can see how it's kind of zooming in on the different layers because each layer somehow corresponds to a different level of approximation. So I have 5 more minutes, I guess. Yes. So very quickly, I could just mention this. So of course, everybody's heard of GPS. GPS is a messy thing. There's about 32 satellites, around 20,000 kilometers, moving very fast. And they broadcast their time span rotation. There's competitors to GPS, particularly GLONASS in Russia, and Baidu 1 and Baidu 2 in China. Actually, if you have any iPhone later than, I want to say, iPhone 4, it can use both GPS and GLONASS. It actually connects to the Russian satellites too. It's really funny. I didn't know that. And now Galileo in Europe, that is still under construction. So this is a messy thing, and of course, based on the location of the satellites, you can figure out where you are. Right? They come in many shapes and sizes. Everybody has one in their pocket, but there is a problem. Right? This is somehow it's approximating the world as being a sphere. The world is not exactly a sphere. Right? The world kind of actually looks a little bit more like a potato, which is not exactly a sphere. Right? So, and this means that if you want to do very precise measurements, you have to adjust this, and you have to model the world not exactly as a sphere, but more some type of an ellipsoid. Right? Then there's no point to go into too many details here, but basically there's different ways. So there is something called the geoid, and this is basically the sphere. The ellipsoid is the ellipsoid of the thing, and then you have the actual surface of the Earth, which sometimes will be above, sometimes will be below. And especially if you want to look at altitudes and that type of thing, you have to be careful. The standard ellipsoid that people use is called WGS 84. This is a standard. This defines basically a very nice, well-defined ellipsoid that is kindly correct most of the time. And this is basic, and you'll see this reference. You can get all the details if you want in that PDF, but this basically gives you the most practical definition of what the world actually looks like and how you can use it to measure distances, right? So this will be particularly useful if you want to use to measure distances between points, right? Because you can see that if you have a sphere, the distance between the same two pairs of coordinates will be different than if you have something that's a bit flattened or a bit stretched out, right? So this will have an impact. This is the standard that uses, was defined by the US military around 1984, for obvious reasons. And this is used basically everywhere. Now, there's two types of data systems, two types of basically data formats for GPS, for GIS systems, so geographical information systems. You have vectors and you have rasters, right? So they both have different types of data. In vector files, you define points, you define vectors, you define lines and polygons. In raster, you can think of raster as being basically a big matrix. So you have cells or pixels and elements, so areas. Here you can define discrete shapes and boundaries. So you're defining literally the boundary. Here you're defining basically the entire value of the matrix, right? Each cell of that matrix has a value. This is very good for spatial database and network analysis because it makes it easier to do some type of operations. This is better for spatial analysis and for modeling. Here the formats people use tend to be shapefiles, which we'll talk about in a second. GeoJSON will also talk. The others. GML is actually what Google Earth uses. Here in raster there is GeoTIFF, there is Ascii, there is JPEG 2000, etc. But you can think of this as basically being matrices or images, right? So you have pixels. In particular, we're going to talk a little bit about Ascii, and this is literally just a matrix. You define a matrix, you define the coordinates of the lower left corner, you define how big each cell of the matrix is, and that basically gives you a grid over the world that you can use. And that's very, very useful. So let's start by looking at vectors. Vector data types. There's, of course, vector files define geometries. Geometries can be line strings, can be points, can be polygons, or collections that have multiple lines, multiple points, or multiple polygons. A few fundamental concepts. So if you have an object that kind of looks like this, this green arrow area, the bounding box is any rectangle that encloses that object. There is something called the minimum bounding rectangle, which is the smallest rectangle that encloses that thing. In practice, people tend to mix up bounding box and minimum bounding rectangle. They tend to use the two interchangeably, which is not strictly correct, but it's what people do. And then, of course, you can have things that are inside the bounding box, but not inside the object or the MBR, inside the object and the MBR, inside the MBR, but not inside the object, etc. A special reference identifier basically will map, and that's kind of what the WGS84 is, maps the latitude and longitude into this curved surface that you can then use. This is especially important to measure distances. Rectangles make it easier to quickly check relative positions, so if you can check very easily if it's something is inside the rectangle, inside the bounding box or not. But it makes it hard, they lack precision, right? So the object B here is inside this rectangle, but it's not inside the object. C is within the shape, etc. If the bounding boxes don't overlap, you're sure that the shapes don't overlap, right? Because the shapes are inside the bounding boxes. Which means you can simplify your analysis a little bit easier. So this is a simple function. So you see bounding box to mean MBR. The MBR you can uniquely define. So you basically have to look at what are the extremes of the coordinates that define the polygon. The coordinates are simply the extreme values, yes, in north, south, east, and west. And GeoJSON is basically a JSON object that is specially formatted with a few more constraints. It will define the geometry, the feature, and the feature correction. Geometry is basically a region of space. A feature is an object that is inside that geometry, and the feature correction is just a list of features. And this supports all types of data types, and it's widely supported, and it's very open standard online, so you can handle everything. So this is what it looks like. It's basically a dictionary that has 3 fields: type, CRS, and the feature. CRS is basically what is the reference system, the coordinate reference system. So that will be so that will be like this is EPSG, it could be WGS84 before. Feature, and then this is the type, so it's a feature collection, so it's several different features. And the features just list everything, so it has geometry, coordinates. So if you're paying attention, you recognize that this looks very much like the results you were getting from the Google Maps API. It's exactly the same thing. And of course, for each feature, you can have associated with it some properties, some data, like an ID, an area, a length, etc. And actually, in GitHub, it actually supports it directly. So if you have a GeoJSON file, like you do inside this directory, it will actually show you on the map what it looks like. It's really cool. And I think we can break here for the second part. Yes, before it's too late. So thank you. So like I was saying before the break, GitHub actually supports directly GeoJSON, and many online services and websites support it directly. So in GitHub, you can just go navigate directly to the file, and it will show you a map representation of the file. In this case, what I have here is basically just a map of Europe, of the countries in Europe. And actually, the countries that have some type of connection with the European Union space. There's also this service called geojson.io, which can allows you to draw a JSON, to generate a GeoJSON file by selecting specific features manually and adding them through a table, etc. And even this one is called GeoJSON lint, that basically lets you check the validity of the file, if it's correctly done or not. See that it's done correctly and that it has no errors. So given a GeoJSON file, it's like I said, it's very easy to calculate what is the bounding box, and in this case, what is the minimum bounding rectangle. So all you have to do is you go through, you grab from the geometry and the coordinates, you just get the maximum of the coordinates along each direction, and that gives you the bounding box, right? The maximum latitude, the maximum longitude, the minimum latitude, and the minimum longitude. So this returns box, and here is the rest of the program that opens the file. So this is a file I got from the European Union website, if I'm not mistaken. It opens it up, and basically what it does is this one has, so this is just as an example, it grabs the goes through all the features in the file, and it extracts the features at each layer. Right here, they're identified as different administrative regions, so it has countries, and then like the equivalent of states or provinces, cities, counties, etc. And so this is layer 0, 1, 2, 3, and that extracts each layer into a different file. So what I showed you before, the map, was just layer 0, which is the country level. Yeah, it just goes up here, and just to show you how it works, and then after it does all of this, it just prints out a file for a specific country, which in this case is Greece. And I chose Greece because it has a bunch of little islands and little things, so you can see how this works. Hopefully, I won't kill the internet again anytime soon. And as usual, it opened in the wrong window, but that's okay. Here it is. So you can see it basically, each feature is a polygon, and here it's just printing each polygon as a different color. So you can see that generating them all by one. So you have the continental area, you have Crete over there, you have Santorini, etc. All of the big islands. So this is GeoJSON. I said it's very simple. It's just JSON. It's just a dictionary. You can manipulate it any way you want. It's very simple. Another one that's much more sophisticated is called shapefiles. Shapefiles, you can think of them as basically being a database. Where you have tables, each feature, each area, each defined object has fields associated with it that give it properties, which can be for instance, the country name, the population, income, whatever you want, any type of feature that you want to associate with it. You can even join different tables to add more data to specific ones, to select data, you can do all sorts of things. This is an open specification that was actually developed by a commercial company called the SRI. They're still the current leader in commercial GIS software. They published the ArcGIS software, which is extremely expensive and not particularly good. Shapefiles aren't actually individual files. Even though they're called shapefiles, they're actually a set of files, usually 4, 5, 6, 10 files, depending on what features the thing has. The actual set of files changes depending on the contents, but there's basically 3 files that are usually always there. You have the dot shape, and this is actually called the shapefile, which is kind of weird, that actually has all the geographical information. So this basically means all the coordinates for all the points, for all the polygons, for everything. The .dbf file is basically a database. It's literally a database. It's a table in a database. And the .shx, it's a spatial index, so it's not strictly required, but it makes accessing specific features faster. So what I actually use instead of ArcGIS is called Qgis. So this is an open source version. It's available in Windows, Linux, Mac, any type you want. And you can, literally will show you, I'll show you, make a little bit of a demo. This, the shapefile I'm going to use is the one for the official one for New York City that I got from City Hall, that just has the 5 boroughs, so the 5 big neighborhoods of New York. So you have Manhattan, Bronx, Brooklyn, Queens, and Staten Island. And now let's see this actually working. You can see it, but it's actually opening here. Here we go. Where is the, okay. So this is what it looks like. And you can say, let's see, layer, add layer. So this works in terms of layers. So you can think of layers as being cards in a deck of cards, on top of each other, and you can shuffle the order, and this impacts what is visible and what is not visible. So I'm going to add a layer. It's going to be a vector layer because it's a shapefile. I'm going to browse. It's in teaching. It's in Brazil. So this is all the files you have in the GitHub. So it's inside GeoFiles. NYBB, and then YB.shape, which is this one, yes. So you open it, and poof. So now you can see that you have exactly the entire city of New York. You can see also that it has the 5 different areas, so Staten Island, Manhattan over here, Bronx over there, this is Queens, this is Brooklyn. In particular, you can also see that even though these are 5 pieces, each here, if you select one, you actually have sub-pieces because you have little islands that belong administratively to the other one. So if you select here, for example, you have a bunch of the little ones. Manhattan, you actually get Roosevelt Island over there and a bunch of the little ones over here, and even the piece of Bronx over there for some reason. Each of these has, which you can't really see here very well. Let's see. I'm trying to get out of, I was trying to show you here, but these are basically the properties that you have associated with it. So each of these objects, in this case a borough, conceptually corresponds to a row in the database. This row can have multiple fields. In this case, it has the name of the borough, an ID, the name, and the area, if I'm not mistaken, which you can't see because it's hiding over there. And it's cutting it for some reason. Let's see. And if you could see it, then all the fields associated with that are hiding in the corner. So let me wait. I can do, maybe this will work. Here we go. So now you can see a little bit better. So you can see there's an ID that's hiding over there. There's Manhattan, and there's a couple of numbers. If I select a different one, you will see. So this is Staten Island. It's called Staten Island. Has a different ID. There's a different bunch of numbers. That's Queens. That's Brooklyn, etc. Now let's close that. So I can escape. For some reason it doesn't let me escape, so don't save for now. And based on QGIS, you can have different layers on top of each other. You can merge the layers. You can check what features on one layer correspond to another layer. You can load data from a different database or a CSV file and do a join of the different tables so that you add more fields to each of those elements, etc. But of course, what you want is not to do this by pointing and clicking. You want to do this programmatically. The way you do that in Python is you use PyShape. PyShape defines basically a bunch of utility functions that load and manipulate shapefiles programmatically. So this lets you basically open the shapefile, look at what it has in the database. You get all the coordinates and all the points if you want. You can select anything. The shapefile module. So this is the package. This is the module that it's defined inside the package. And does the most common operations. Reader will return a reader object, and it basically opens the file so that you can read it and manipulate it. Reader records and reader iter records returns the iterators over the different records. In the file I showed you before, each borough was a record, was a row in the database. Each row in the database also has a corresponding shape. So this is the actual polygon that represents the shape geographically. So if you can ask for the shapes or iterate over each shape, and here the same thing. We get all the records, iterate over the records. You can also get the shape records, which basically gives you one object that contains both things, the record and the shape that's associated with it. Or you can get one directly. So index is basically which line of the database you want, which row of the database you want. And reader.numRecords basically tells you how many rows in the database, how many records in the shapefile. And you can see it working here. So you can see it's very, very simple. So just import the shapefile, which is the module you're using, shapefile.reader. This is the file we're going to use. Print, it has 5 records, this is what it say. Here what I'm doing is creating a simple dictionary that associates the record value with the name of that record. So basically, the name of the row, the name of the column with the value in each row. And then and I'm basically printing out the ID field. That's what I'm doing. So you can see this here. Wait, what was the name of the file? Shapefile load. Poof. It says it found 5 records, and these are the records, that's the ID, and that's the name associated with each of them. Right? And these are the ones I showed you in QGIS. Questions? No. PyShape also defines a shape, which is another type of object, and this basically defines a geographical area, which can be a multi-polygon, so it can be a series of polygons. So like in Manhattan, you have different islands that belong to Manhattan. But those all represent the same shape. The B box, so this is the bounding box. The lower left and upper right XY coordinates. So again, longitude, latitude, not latitude, longitude. And this is optional, so it may or may not have it depending on the file. Part is a list of indexes for the first point of each of the parts making up the shape. So this is a very convoluted way of saying that you have a list of points, and this part tells you from which point which item on the list belong to each shape. Right? So you can select them out. And shape type basically tells you what type of shape it is. Every shape must have a type, so it can be a point, so just point. It can be polylines, so just disconnected lines, polygons, multi-points. Point Z, polygon Z means points in 3 dimensions with the Z coordinate, the altitude, etc. So here's another example. So again, I'm reading the file. I'm iterating over all of the shapes. I'm getting all the points for each shape. I'm converting into a NumPy array. This just gives me the part. I'm adding the total number of points to the part just for simplicity here. And here I'm just printing out basically the lines for each shape. Right? Because the parts basically tells me where in this list where each shape begins and where each shape ends. So I can just say this is one shape, this is another shape, this is another shape. And saving that to that file. So when I do this, this is basically the program I used to generate that picture of Greece I showed you before. So it's similar to the GeoJSON. Here it's the same thing, actually. So I can just do version. And apparently didn't do anything, but it actually did. It generated. Uhum. Sim.
E aí, para cada camada, você tem que definir protocolo para analisar aquela camada?
Sim.
Se vai ser um polígono, se vai ser
Exato. O que é na camada? Neste caso, são todos polígonos, porque estão a definir uma área geográfica. Né? Ou melhor, são multipolígonos, multipolygons, porque é uma área geográfica, mas é desconexa. Né? Tem várias. Manhattan tem várias partes, não é uma parte só. Isto foi a imagem que generou, que o programa generou ali. Here's the image again. So Shapely. Now Shapely is another library, another Python module that was created to manage shapes. This gets a bit confusing because everybody calls different things the same name, so it gets a bit confusing. But basically, this is a way of defining geometries. Right? So you can already see that it's very useful. You can grab the shapes from the shapefile, feed it to Shapely, and then manipulate them from there, which is exactly what you're going to use. Shapely defines geometric objects, so as usual, they are points, polygons, and multi-polygons. So these are the basic GIS object types that we saw before in that little hierarchy. The .shape function is a convenient function that basically creates the appropriate object given a list of coordinates that you get directly from the shape file. And it defines a bunch of common operators, so it can tell you if one shape is on top of the other, it can tell you if it's inside the other, so if it's contained, if it's within, if they're only touching, etc. So shape objects will give a bunch of useful fields, so they can also give you information about the shape that they define. They can give you the centroid, so the geographical center. They give you the area, the bound, so this is the bounding box or the minimum bounding rectangle, the length, so what is the perimeter of the shape, the geometry type, so what type of geometry it is. And Shapely.shape actually is able to load by shape objects directly and convert them automatically. Right? So we will see that here. So again, we're doing the same thing. We're opening the shape file. I'm getting my little dictionary, so I can just say, give me Manhattan, and get the shape of Manhattan. And get it from the shape file, feed it to Shapely, and get the Shapely object. And then I can ask questions about this. I can ask where the centroid is, what are the bounds, what is the geometry type, what is the length, etc. So it loaded the shapefile, it calculated the centroid, it calculated the bounding box, it gave me the geometry type, so it's a multi-polygon, what is the perimeter, what is the length of the shape, etc. Now, doing this, one thing that's also useful is you don't want to just define areas. You want to see if some points are inside the shape or not outside the shape, right? So you want to filter points based on whether they're inside the shape or not. Right? So in particular, one of the things we can do is look at tweets and filter out. So you already saw how you can search Twitter for tweets happening inside the box, inside a rectangle. Now we can refine those results and say, instead of giving me, look at all the points I have and filter out the ones that are inside this arbitrary shape. Right? So I can filter out, for example, the ones that are inside Manhattan only. I already showed you that I gave you a file with 10,000 geolocated tweets inside the bounding box for New York. Now I'm going to read all of those, and I'm going to filter out the ones that are inside the Manhattan, defined arbitrarily by this shapefile. Right? So, and this is basically what it's doing. So again, it's reading the shapefile, it's generating my funny little dictionary, it's selecting Manhattan, then it's opening a file, it's reading the file I gave you before, parsing each tweet, extracting the coordinates, checking, converting the coordinates into a point, checking if the point is inside Manhattan, and if it is, it writes it to that file. Right? So just reading one file, checking if it's in where we want it, and if it is, it puts it to the other file. Right? What was that thing called again? Shapefile filter. So it takes a little while to process, but it will generate basically the file on the other side. And you can see basically it generated 433 just now, generated a new file based on the old file that's hiding somewhere below. So that file contains now only the tweets that are inside Manhattan. And you can check that indeed we have filtered out things. So before we had 10,000 tweets. Now we have 940. Because it discarded all the other tweets that we're not interested in. And you can see what it looks like. So now, basically, that's all the pieces of Manhattan, and each little cross is a tweet. And it's a tweet defined by the latitude and longitude as seen inside the geo field, like I defined in the beginning. Dentro desta área aqui, destas áreas aqui. Tenho alguns aqui, tenho outros aqui nesta ilha pequenina, tenho outros ali. Now, as I mentioned also in the beginning, besides the geo field, there's also something called the places field. Right? and places, what it gives is not latitude and longitude, but it gives you a different level of precision. So, and this is, the source for this is a bit unexplained, let's say. But the places field, what it does is it uses geolocation based on other sources that are not GPS receivers. Right? It can be your IP address, it can be where you happen to be, if you're checking into a specific place, if you're declaring to be in or if you're tagging or checking into a specific location, etc. So this will be geographical information, but it's a coarser resolution. So it doesn't have actual latitude and longitude, it has bounding boxes. Each place has a unique place ID and the bounding box, and some geographical information, as well as the country it belongs to and the full name. So this is the bounding box for Brooklyn. So it tells you it's Brooklyn, it tells you it's a city, gives you the ID, the full name is Brooklyn, New York, the country code, so which country it belongs to, and it gives you a bounding box, so the little rectangle where it is. And places can be of different types. So here you see the place type is a city. They can be an administrative region, so it should be like a state. It can be a neighborhood. It can be a POI, means point of interest. So this is basically usually some type of touristic location. So this will be the Eiffel Tower, the Statue of Liberty, the Empire State Building, etc. So, and particularly useful, of course, are the bounding box and the full name and the place type. And the bounding box, coincidentally, is actually a GeoJSON formatted, right? So you can just parse it to anything that handles GeoJSON and it will be happy. And in particular, PyShape.shape will be happy. So you can check if it's inside, if you have points inside that shape or not. The place field is actually particularly poorly defined. It can have all of these fields or not. All of these are optional. Yeah, because this is the official documentation from TTSS. May or may not exist. So maybe they're there, maybe they're not. So you should always check if you're relying on them. First. The URL, also if it's, for instance, a point of interest, might, like the Statue of Liberty, it might give you the URL of the official Statue of Liberty website, etc. So this is a modification of the previous file that basically filters not only latitude and longitude, but also for using the places field. Here, I'm cheating a little bit, and I'm looking at the places field. I'm grabbing the bounding box. I'm calculating the centroid of this bounding box, and then if the centroid is inside the shape I want, then I define it's inside that shape, or I accept it. So it's a very simplified analysis, but you get the idea. So reading the shape file, getting my dictionary, selecting Manhattan as before, opening my New York City file where I have all the tweets. If I have coordinates, that's great. That's what gives me the point. If I don't have coordinates, I look at the place field, and if I have a place field, I grab the bounding box, I calculate the centroid, and that's my point. And then I check if the point exists, and it's inside Manhattan. If it is, then I save it. And now this will go inside Manhattan places. But you can see it's basically the same idea. I'm just obtaining the point that I'm comparing with in a different way from a different place. It'll take a little bit. Also, this is a good demonstration that it shows that every time you're manipulating shapes and you're comparing if things are inside shapes or not, this takes time. This is known as the point inside polygon problem. So to check if a point is inside a polygon, you have to compare the position of that point with the position of every point that defines the polygon. So which in this case is thousands of points. So for each tweet, you're doing thousands and thousands of computations, so it takes a long time. This is why it takes a lot longer. Right? So running this filtering for the places takes much longer than filtering just for the coordinates. It takes much longer than not filtering for anything. Again, we check that the file got generated. Manhattan places, you can see it's bigger. You can even check how many lines it has. Okay. Oh, because I put a space there. Should be no space there. And now you see that we went from 940 tweets to 2,675. Right? So you already increased a lot the amount of data we have available just by doing this small change. Of course, this small change computationally costs a little bit, because you're doing more computations, you're comparing one point to a few thousand points, so it takes more time. But CPU time is cheap, usually. And in the end, you get almost 3 times as much data, which is a good thing. So now this is what our points look like, so you can see it's much denser. And this is the program that I'm using to plot, to make those little images with the shapefile and the points. Right? So you can see it's very simple. So you should already know more or less how this works. read the shapefile, select Manhattan, because that's the only thing we're plotting, get all the points of Manhattan, get all the parts, append the number of points to the parts file, and then print basically all the polygons that define Manhattan. That's easy. And then open the file. For each tweet in the file, check the coordinates, check if they're inside or not. So this is what we're just doing before. And if you have a point and it's well defined, you just print it. Already add it to the list, and then you plot it at the end, and just save the file with the same original file name plus .png at the end. So if you do this, for instance, Manhattan places, because it's the smallest one, so it will be the fastest. Generated the .png over there, and here is the image, which is exactly the image I showed you before. Now, what have we done so far? We've collected data, we've extracted the data, we've checked, we've defined the boundaries using a shapefile, we've checked if points are inside the shapefile or not, if we can see if different shapes are overlapping or not, etc. One thing that's also useful is calculating distances. Measure the distance between 2 points. Right? As we saw, at some point, the distance between 2 points depends a lot on how you define the world. If you define it as a sphere, or a geoid, or an ellipsoid, or any other way. We can also, of course, define the distance between 2 points using the Google Maps API. Here, the problem with this is Google Maps API will give you the distance in terms of drive distance, not the shortest path distance. Many times what we want is the shortest path distance, especially between arbitrary points on the surface of the Earth. For instance, there is no driving path distance between Brazil and Portugal. There's an ocean in between you can drive. This depends strongly on the model of the Earth. Grid circle just says that this is a perfect sphere, and you measure around the sphere. Also known as the Haversine formula, which takes the latitude and longitude into account, basically and the radius of the Earth to calculate that. The Vicenti formula uses a more accurate ellipsoid, so it's a little bit more deformed so that it matches that potato picture I showed you before. And GeoPy is the library that does this for you. And so it defines the distance functions. Instead of you defining them by hand, which you can, of course, if you're a masochist, GeoPy just does it for you. And it gives you geocoders, which we won't really talk, but basically this is similar to what I showed you with Google Maps. It just geocodes, turns addresses into locations. And it lets you use Google Maps, nominate them, which is the OpenStreetMap one, Yahoo one, Bing, etc. And GeoPy.distance, which is the one we're interested in, basically gives you the state-of-the-art definition of how to measure the arbitrary distances between points. We will focus just on the distance module. Distance Vicenti P1, P2 calculates the Vicenti distance between P1 and P2. Distance grid circle P1, P2 calculates the grid distance circle between P1 and P2. That's easy. And distance is the default, and it's an alias to Vicenti because that's the most precise one. And they try to always use the most precise one. All distance functions give you a distance object, which is kind of redundant, but it's true. The distance object provides properties that represent the result in different units. Right? So given this object, you can ask for conversions to different units. You can ask for kilometers, you can ask for meters, miles, feet, nautical miles, and I think that's it, yes. It also allows you to recalculate the result using different ellipsoids. So if you get the result in one ellipsoid, you say, no, but what if I want it in that ellipsoid? And they will do the conversions for you. So you can set the ellipsoid. By default, WGS84 is used, which you know how it's defined already. So this is how the code to use GeoPy looks like. So here I'm calculating the distance between these 2 points. The Vicenti distance is calculated by this. The grid circle distance is by this, and I'm printing out both. Here I should emphasize that this is doing everything locally, so it's not connected to internet, not doing it. Everything is calculated in your computer. So you can do this as much as you want, which is very useful. which is something that you can't do with the Google Maps API, of course, because you have to contact Google Maps every time, and you have limitations to how many times you can do that. And you can see here, so this is the vicinity distance, this is a great circle distance, and you can see that there is a difference of about 1 kilometer or so, 1.2 kilometers or so between the two, which may or may not be significant depending on what you're doing. So that more or less terminates our view of this vector type format. We saw GeoJSON, we saw zip file. There's also the raster ones, which are also very useful, where you define cells and pixels or elements. These are good for dense data and continuous surfaces, useful for spatial analysis and modeling. And in particular, we're going to focus on the Ascii table. And this is literally just a matrix. I will show you this in a second. So the Ascii grid, not the Ascii matrix. This is the simplest possible raster file. It's literally a table of numbers. It's ASCII text-based, so it's very easy to generate. It has a small header in the beginning of the file that basically defines what this matrix is representing. So it tells you how many columns and how many rows the matrix has. It tells you the coordinate, the x and y coordinates, so the longitude and the latitude of the lower left corner, right? So if you have the matrix like this, it's telling you what are the coordinates of this point here. It tells you what is the cell size. So when you move from one element of the matrix to the other, how much you are moving in coordinate space. And this is the same size in both x and y directions, in both latitude and longitude. And how you're defining null values. So if the matrix element is not initialized, if there's no value, what is the default value? And which in this case is minus 9099. And this is from a file for the US population that basically gives you the big raster file, and each cell of this file tells you how many people live there. And after this little header, what you have is lines. Each line corresponds to a row of the matrix. Each column is separated by a space, so just have one number, space, one number, one space. And you have these many columns, these many rows. And so it's very convenient to read and write. And this is how you'd read it, right? So this is just a commodity function I'll mention in a second. So here I'm opening the file. I'm getting the number of columns here. I'm converting it to an int, getting a number of rows, getting the lower left corner longitude, the lower right corner latitude, the cell size, what is the no data value, so what is the default value. And then after I do all of this, I'm at the beginning. I went through the entire header, and now all I have is my matrix directly. So for each line in the file, I split the line in spaces, I convert the values to floats, and that gives me a row of my matrix. Here I'm just doing a list of lists in Python. Then I'm converting to a NumPy array. I'm just for convenience setting that if all the cells that have the default value, I'm setting them to 0 because they're not interesting. And this is just an arbitrary point. And this function that I kind of ignored in the beginning, what this is doing is basically converting latitude and longitude to coordinates on this matrix. Right? So if I want to map an arbitrary point to a cell of the matrix, this is the simple function I have to use. So basically I have to subtract the coordinates of the lower left corner and then divide by the size of the cell. Right? It's as simple as that. And then I'm since I want the actual ID of the matrix cell, I'm converting to int. Here you have to do it upside down because basically line 0, the first line of the matrix, does not correspond to your point of reference, so you have to kind of flip the reference frame. So that's why you do n rows minus 1 minus this transformation, but it's the same thing. And if you do this, yes, so I'm just highlighting that piece over there. You're basically just loading an arbitrary ASCII grid file, And I'm not showing it here, but then you can just plot it as you plot any other matrix or any other image. And what you would get is this. Right? So this is the population of the US, the continental US. And here there's a little trick, which I'll show you. Because you have the population has a very wide range, and it goes from 0 to several million, potentially. What I'm actually plotting is the logarithm of the population. So that's why you see the scale goes to 14. It's logarithm base 2, if I remember correctly. And I'll show you how to make that figure in a second. So the type of grid, so this type of grid is very convenient because it's just a matrix. You know how to add numbers to a matrix, how to manipulate matrices. You simply have to map the latitude and longitude to cells in this matrix. All you need is to define the bounding box, and that's it. And create a matrix of that shape. So if you want to generate one of those things, one of those Ascii grids, this is all you have to do. Right? So here I'm doing one for Manhattan. I'm reading the shapefile as I was doing before. I'm selecting Manhattan as before. I'm getting what is the bounding box for Manhattan, because that's the area I'm interested in. I'm defining my cell size, calculating how many columns and how many rows I need. So basically, from the bounding box, how I'm dividing it into a grid. And then I'm generating a matrix from that, and that's it. So all of this is doing, and then at the end it just prints what is the number of rows and number of columns. So it's a very simple thing. And in that case, for that definition, it just has 19 rows and 14 columns because it's a very small area. Now, of course, you don't just want to generate a matrix of zeros. What you want is actually use it to aggregate some type of information. Right? So here, what I'm doing is the next step. Right? So you can think of it as, if you think about it a little bit, it's already something a bit complex. No? I'm reading a shapefile. I'm selecting a piece of it. I'm generating a matrix based on that piece of the shapefile. I'm initializing it with zeros. I'm reading all the tweets I have in my file that in this case would be the Manhattan file, if I'm not mistaken. I'm incrementing the values of this matrix, and I'm saving it as a raster file. So, and I'm doing all of this in a small piece of. So this is already the same function we saw before, just a way of mapping points to cells in the matrix. This is a utility function that basically saves my matrix as an Ascii grid file. So it writes the header, and then it just writes the rows and columns of the matrix. So it's very simple. And this is where all the magic is happening. Right? So again, it's reading the shapefile, selecting Manhattan, getting the bounding box, setting the cell size to be 0.01, the number of columns, calculating number of columns, number of rows, generating my matrix. Right? So this is what we had already seen. Now, it's opening the New York City shapefile, grabbing each tweet. If the tweet has coordinates, it uses them. If it doesn't, it looks for the place field, looks at the bounding box, calculates the centroid, and then if that point that we get either from the coordinates or from the place is inside Manhattan, it calculates which cell of the matrix it belongs to, and then increments the value of that cell. Right? So it's doing all. So it's in a sense it's very complex, but in the other sense it's very simple. Right? It's just counting things. All the magic is happening here. Plus equals 1 is the magical line of code. And then it's doing all of this, saving it as manhattan.ask, and then it's plotting it. And like I said before, I'm plotting the data +1. Here I'm setting +1 because I'm going to take the logarithm. And you can't take the logarithm of 0, so I'm adding 1 just to shift everything a little bit. And then when the logarithm is applied, that becomes 0 again. And then I'm plotting with a color bar and saving it as a file. So I can see how that works. É uma rede, né? E é o tamanho de cada célula da rede. Okay, what is the name of the file? Shapefile file. filter aggregate. So Python filter aggregate. Takes a little bit because it's doing all sorts of things, loading shapefile, generating the file, all sorts of magic happening. But you can see that even something that is conceptually a little bit complex can be written in a few lines of Python. Right? And it's not even the most efficient or compact Python code in the world. It's very, very simple. And it's done, which means that now we should have 2 new files. And we do. So we have the Ascii Grid file that we created, and we have the picture we generated from it. We can see that this is what the file looks like. So it's literally just a header, and then columns of numbers. You can even see where the kind of the shape just from looking at it. And here is the histogram of all the tweets happening inside Manhattan in that file I was using. So you can see immediately the shape of Manhattan. You can see basically where most of them are happening. Of course, if I made the cell size smaller, then you get more resolution instead of these blocky things. These would be smaller. Right? So instead of 0.01, I put 0.001, then you'd have a much nicer picture, but it would be mostly empty because I had very little data. And yes. So, and this is the image, that's why I always show you. Now, of course, sometimes what you want to do is you don't want to show just some blocky thing like this. You want to put the shapefile also on top of it. You can do that too. So I'm hiding a few functions over there, but basically is the definitions of the functions I already showed you before. I'm opening this Ascii Grid file I got here. I'm showing it in the image like I showed before with the data +1, logarithm of data +1. I'm opening the shapefile. For each shape in the shapefile, I'm plotting basically the lines around it. And here is just a trick to add the lines around it afterwards in the red continuous line, and then I'm saving the figure as US overlap.png. So let's close this. That's not shapefile overlap, what's it called? Matplotlib overlap. It didn't explode either, so that's good. I generated a new file called US overlap. Which again opened in the wrong window, but here it is. And it's exactly the same image I showed you before, but now I'm overlapping the boundaries of the states on top of it. Right? And of course, I'm doing this in a very simple way. I'm not trying to make it pretty or in any sense of the word. I'm just trying to show you how it works in the simplest possible way. And yeah, so here it is. Matplotlib also has, and this is the most basic plotting library for Python, also has a basemap module. Basemap lets you plot maps and project maps in pretty much arbitrary ways. It's the workhorse for mapping. It returns a basemap object. The basemap object has many useful methods. Whenever you can draw coastlines, you can draw map boundaries, so it knows more or less the boundaries of the continents and the countries where the oceans are. You can fill the continents to add colors, etc. The constructor for base map can take many, many different arguments. It's a world of its own. It defaults to plat carré. Plat carré is basically a fancy name for what we've been using, where you just have latitude and longitude in the same scale as x and y coordinates. And the projection is centered at 0, 0. 0, 0 actually is a very special set of coordinates. This is called the null island, and you see it many times when people are not careful plotting data that they're geolocated data that they're mining. And you see a bunch of points more or less on the armpit of Africa, where Africa kind of does like this. There's a bunch of points right there, and that's 0, 0, just off the coast of Nigeria. So if you see, whenever you're plotting these things, if you see points in the middle of the ocean next to Nigeria, you know you have no points. The minimal map, so this is, all you have to do is this, gives you the map, draws the coastlines, and that's it. And you can, actually, I don't think I have that. And it basically just shows you a map of the world. It doesn't do anything special. Without draw coastlines, it doesn't have anything because everything is the same color and there is nothing to contrast. You can also ask for specific regions. So you can say, give me just the map in this box. And here the notation seems a bit scary until you kind of try and parse it. So this is the lower left corner longitude, lower left corner latitude, upper right corner longitude, upper right corner latitude. So here and here. And let 0 and non-zero, so basically this is where you want to center it. You can also convert arbitrary. It also has a very simple function that kind of does what my map point function was doing. It converts arbitrary latitude and longitude to coordinates on the figure. And after you obtain the map coordinates, you can just add them by calling the plot method. So you can plot arbitrary things on top of the map. And you can do this in any type of projection you want. So here is a simple example. So this is base map example. So I'm opening the base map with an orthogonal projection centered at 0, 0. I'm drawing the map boundaries, and I'm putting the default color to be aqua, so light blue for the oceans, basically. I'm filling the continents with coral and the lakes with aqua, so it matches the thing. I'm drawing the coastlines. I'm converting the x and y, the latitude and longitude 0, 0 to x and y coordinates. I'm putting them on my map with the little marker, with the diamond, with this color, and I'm saving it as globe.png. And if you save this, because I forgot the W there. Oh yeah, because something got deprecated that I haven't updated yet, but it still works. And then open globe.png. And what you get is this. Right? And I just plotted the null island, which is the little thing on the armpit of Africa. And with this, you can make any type of projection you want. You can draw anything you want on the map, on the globe, anything. Of course, different projections will take different arguments, and you have to look up the documentation. But basically, with this, you can pretty much do anything you want. And you can even zoom in, which is kind of cool. Let's close that one too. And now, by special request, we're going to switch a little bit and talk about Wikipedia. Wikipedia is also a huge source of information. Of course, I'm sure all of you use it more or less directly, more or less daily. You have pages about all sorts of things. Cities, people, locations, Pokemon, anything you want to know. You can also, for each page, you can get all the revision history, so all the versions of that page. So it's completely version controlled. So you can see who made what change and when. You can also have user information. What is who are the users? What is the profile of the user? What do they like? What they don't like? And this is completely arbitrary. The user can write itself whatever they want. There is also There's also bots. The bots, according to the rules, have to be self-identified as bots. So they're easy to detect and easy to filter out if you don't want to see what they're doing. So they have to identify them with the bot in the name. They have to have a bit flipped in their profile, etc. So they have to be marked as bots. And in particular, you also have the talk pages, right? So these are pages that discuss proposed changes to other pages. So they're like the meta discussion. So in the case of, so for instance, in the case of Turin, so this is a city I go to often in the north of Italy. There's this big discussion between should the page name be Turin or should it be Torino. Turin is a name in English, Turin is a name in Italian. They say that this is the English Wikipedia. Some people say this is the English Wikipedia, so they should use the English name, which is Turin. The other argument is when they had the Winter Olympics there in 2006, the logo was Torino 2006, so people recognized Torino as meaning that, so maybe they should use Torino, and they've been arguing about it for a while now. They've been fighting over it. And you can see all of these discussions, and you can see all of these things. So basically what you have here is a platform where you can obtain all the data you want. Everything is completely public. And it's a collaborative platform where people are organizing and cooperating to generate content and high quality content. And of course, this creates dramas, this creates fights, this creates editors, and all of these things can be analyzed very easily. Now, there is an API for Wikipedia. The API, you can ask for permission. It's very easy to get. Usually takes a while because people are lazy and don't answer you quickly enough. But you fill out a little form online. Usually in a couple of days, you get an answer that says, okay, you have been approved, and then you get access to their servers. This basically gives you SSH access to a node that is connected to their MySQL database, so you can run arbitrary SQL queries in a copy of the database so you don't interfere with the thing. This is extremely tricky, and there's many limitations, which I don't like limitations. Now, on the other hand, there is this thing called the Wikimedia dumps. Wikimedia, every day, saves everything that's inside this gigantic database into files and publishes the files. And every day you can download these files if you want. You can download everything for every edition, or you can download only specific things. These files in general are a mess. They come in many different formats. They were all generated at some point for some specific function that maybe doesn't necessarily make any sense anymore, but this is the way they're generated. So they have a lot of idiosyncrasies. But you can get everything. So, and I'll show you a little bit how to get a few things that are interesting. Now, Wikipedia done. So Wikimedia Foundation makes freely available regular dumps of everything, in particular for the various language editions of Wikipedia. We have files that look like this, pages, articles.xml.bz2. So this is the complete Wikipedia page and all the revision content as a giant XML file that's bzipped, which is a mess, by the way. Step metahistory.xml is Wikipedia page revision metadata. So this just gives you a little bit of information about each revision. So this is more or less the equivalent of looking at this. So this is more or less the data that's used just to generate this summary. It's very simple. So in case you don't actually need the content of the page, you just want to see how many revisions have been happening, this is the file you would use. There is pagelinks.sql.gz, and this is a MySQL table that contains all the page links from basically all the links between one Wikipedia page to another Wikipedia page in the same edition. You have the geotags.sql.gz. Again, it's a MySQL table that has the coordinates of every page that has coordinates associated with it. So in the case of a city, there will be the latitude and longitude of the center of the city. In the name of a touristic attraction, will be the latitude and longitude of that touristic attraction. An airport will be the latitude and longitude of the airport, etc. This is actually really interesting because they actually have, especially in the English edition, they have points of interest in other planets. So you have like the landing coordinates for the Apollo moon landings, they'll have the coordinates on the moon, and they're kind of defined in a different way. So one of the fields of this table is the planet in which the coordinates are referring to. It's really funny. External links.sql gives you a link, again, a table with all the links from pages inside Wikipedia to outside Wikipedia. .page.sql.gz is a per page data, so this is metadata about each of the pages. Language links.sql.gz are language links. And so what this means is, you've probably noticed on the left-hand side of the table, of the page, at the end it says this page in other editions, and it links to other languages, the same page in other languages. So they are all here. These are particularly messy also because these links are not symmetric, they're actually directed. So if you go on the English Wikipedia, you have, for some specific page, you can have links to many other languages, but if you're in the other languages, you don't necessarily have links back to the English page, so it's kind of weird, but that's okay. And yes. You see that these come in a variety of formats. Some of them are XML, which is a mess. Some of them are SQL. Some are zipped with gunzip. Some are zipped with bzip. There's no consistency in why one and not the other, who knows? In particular, we're going to look at stub meta history. So this is the page revision history, metadata. We're going to look at the geotags, and we're going to look at language links. A little parenthesis on how you can download all of these things. There are over 200 editions of Wikipedia. Each edition has a few dozen files. So you don't necessarily want to go and click one by one and do it by hand. So I wrote a little simple script that basically does these things for you. You can find it in the GitHub as wikidump.py. I won't demonstrate this. There is no point. To customize that you need, inside there is a list of allowed files. So these are the file names that you want to extract. Allowed wikis are basically the editions you want to get. And you'll just do the for loop over all the editions, over all the files, and download them all for you. If you want to download all the files from Ace Wiki, so I chose Ace, I forget which language it is, some random small language, because the files are relatively small, so they're fine. So if you want to play with it, they're easy to download, and these are the files I'm going to use in the demonstrations in a second. So I'm getting the stub meta history.xml, I'm getting the geotags, and I've got the language links for Ace Wiki. But with what you learned so far, you should be able to easily write your own version if you really want to. Now, like I said, many of these files are SQL files. SQL is a mess. If you remember your database classes, they're not necessarily the easiest thing to manage, especially in large quantities. Most of the time, you don't necessarily want to run particularly complex arbitrary queries on this. Depending on the type of analysis you want, most of the time what you want is just want to go down the list, one by one, and select the ones you want, or count, or do some types of simple aggregation or counting. Because databases are optimized for fast querying and these things, but it's not necessarily what you want. So there is another thing that is also hiding in the GitHub. It's called MySQL dump to CSV. It basically grabs the SQL file, turns it into a CSV file. Very easy. It's a slightly modified version of this other thing I found online. And it's, again, available in the GitHub repository. And the first row is basically the column names, which correspond to the field names in the SQL file. Now, language links. This is one of my favorite files. It has just a few fields. The first field, field 0, is LL from. So this is the page in this Wikipedia edition. So this is the origin of the link. LL-lang is the language that it's linking to. So this would be like page 1 in the Ace Wiki edition is linking to the English page. 2 is the title of that page in English. And the tag of the Wikipedia edition, right? So, and if you think about it, at some point somebody generated this in this format because it was a good idea. In practice, it's a mess. Because what you have here is, this is a number, this is a page ID. This is a language edition, and this is a title. If you really want to build a network of these things, for example, you either have to convert the ID into a title and then match the titles, or you have to convert the language and the title into another ID in the other thing and match them. So this is a good example of some of the problems. Many of the file formats and conventions were created, who knows why. How can you convert the language file into page ID? Can you be sure that two pages in text should switch titles? I've never found a case where this happened, but I don't think it's necessarily impossible. As pages get edited, their titles change to which revision do these files correspond to. Usually this is the most recent version, so they're kept more or less up to date, at least as far as I can tell. There's really no documentation for this. So does a link from A to B imply a link from B to A? This is very much no. The links are not symmetric. So let's look at a simple example. So we want to convert this file, which again is in the GitHub under data, to a CSV file, and that's easy. You just do MySQL dump to CSV, or the MySQL dump underscore to underscore CSV. For some reason I misspelled that horribly. So you just have to do this. Excuse me. Which we can. If I didn't forget to copy all the files, this should work. Okay. Now I want data, ACE. Which one do I wanted to do this for? Lang links, of course. And yes. So, and this will just print out things that it converts, and we'll just print them out standard output. So then I want to zip minus C, and then send it to the other file, langlinks.csv. And you can see this will run very quickly, and it went from one file generated to the other. So you can see this file was generated now. And the format is what we expected. So this is an ID, this is the language it's linking to, and this is the name of the page it's linking to. The title of the page in the AA language. These you'll see also that these are, at least here, what you have are mostly special pages. So these are user pages, they're templates, they're categories. If you're interested in looking just at regular pages, then you'd have to filter out pages directly, what type of page you want. That's actually relatively simple to do. No. So that's one thing. Now let's look at geotags. Right? Geotags has a bunch of fields. This is a unique geotag. The first one is a geotag ID, so it's just a unique ID. The page ID is the page ID that tag corresponds to. The globe is, like I said, basically what planet it's referring to. It can be Mars, can be Moon, Venus, Titan. I found a bunch of them. Then you have the latitude, you have the longitude, and the type. So this is basically what type of feature this is referring to. So it can be a city, a railway station, a landmark, an airport, any type of thing. So you start with something like this, you convert it to CSV, that's easy, and then you would, for instance, if you wanted to extract all the latitude and longitude pairs on planet Earth, you would just open the CSV file, split each line in the commas, because it's a CSV file. Here I'm just skipping the header, and creating a dictionary so that the column name maps to what field it corresponds to, so then I can do things like this. So if the globe is equal to Earth, then I'm printing the latitude and the longitude. So and then basically just print out all the coordinates. It's nothing special. Now, on the other hand, many of the files that you're interested in are actually XML files, right? And parsing XML is a mess. The sanest way I found of doing this, especially on a large scale, is to use XPath. XPath is an XML parser. It's written in C, so it's relatively fast, even for XML. So it's well suited to handle very large XML files. And one thing that's very important, it does not try to validate the XML. So it does not try to check that the entire file is correct and valid XML. Because validating XML is extremely expensive. It takes forever. And most XML files you see are not valid XML. They have a typo somewhere that breaks the whole thing. And it's a mess. So this is the best you can do. So it's stream-oriented. You can go line by line because it's not parsing. Every time it finds a tag, it lets you know, hey, look, I found a tag. Do you want to look at this tag or not? It's not non-validating. I already said that. And in Python, it lives inside the xml.parsers package. And the parser create method returns a new XML parser instance. It basically defines the event handler. So that's what I said, when it finds a new tag, it says, hey, I found a tag. When it ends the tag, it says, hey, I ended the tag. When it finds some data, it says, hey, I found some data. And basically what this does is that it makes it very simple for you to define basically a finite state machine that selects what you want. It keeps track of where you are on the XML tree and pick out the fields you want. The default behavior is to do nothing. This is always very efficient. But you can, of course, override that by defining methods that you give to it. Right, so in particular, you want to override the start element handler, the end element handler, and the character data handler. So this is the function that gets called whenever a tag is open. This is what's called when the tag is closed. And this is what's called when it finds data in between two tags. Right? So if you have something like this, first you get called, this one will get called, and you say, okay, I'm starting the tag called name. Then this one will get called and say, okay, here's some data, and then this one will get called and say, okay, the name is closed, right? So if you're interested in filtering out the name tag, you say, okay, I started the name tag, you say, so I have to keep the data I find. You grab the data, you put it wherever you want, and then you close it, and you're done. If the amount of data between two tags is too large, this can happen sometimes, you can get multiple shared data events between the start and the end tag, so you can have multiple things, so it's always good to concatenate them as you get them along. After you overwrite the relevant methods, you just process a file by giving it a file handle. That's it. And it just goes down the file line by line, tuck, 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 and doing everything it needs to do. So here is a simple example, or relatively simple example, let's say. So it's importing XPath. This is a buffer. This is a level. So this is just keeping track of how deep nested it is. So it's doing as little as possible. For each element, I'm keeping it as a global. I'm basically going to change the values of buffer and level, and printing it's opening this tag with these attributes. When the element is over, it says it closed this tag and it found this data. When it finds data, it just adds the data to the buffer. Also, I should mention that whenever a new element is opened, then you clear the buffer, right? You don't care about the data that was there before. And so you can see you're creating a new parser, you're overwriting the start element handler, the end element handler, and the character data handler, and then you're giving it a file pointer, and it'll just do it for you. So you can run XPath demo very easily. And I have a page file, yes, page.xml, you can see poof. So this is literally a page I stole from one of the files. So this is the XML that corresponds to a single page in that Ascii file. So it says, so it's opening the page. It has no attributes. It's opening the title element. it closes the title element and found the title to be whatever that means. NS is the namespace, so this defines what type of page it is. Namespace, the data is 0, so it means namespace 0 means that it's a regular page, so it's not a user page, it's not a talk page, it's not a metadata page, it's not any. So it's what you want. The ID of the page is ID 1. Then it's starting a revision, so each page can have multiple revisions. This is revision ID 1028 that was created on this timestamp, 2008. This revision was made by IP address this. This is the comment, this is a new page, blah, 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 blah. Model, so it's the type of database you want, so this is just a wiki text. The format is the usual format, so you can ignore these things. The text, it has some attributes for this page, which I don't know what those mean necessarily, because these attributes tend to depend also on the different editions, they'll define different things. So if you want to really understand what each edition is doing, then you have to read the documentation, which might mean you might need to know the language, which is not necessarily trivial. It has a hash code that basically you can use to check that it's not corrupted. And that's it. So it closes the revision. Here I just grabbed two revisions, I think. So here's another one. So then it's another revision. So this is revision ID 1029, blah, 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 blah. This was done by username, by an actual username instead of by an IP address. It has a comment removing all content from page for some reason. So now it has 0 bytes. And the hash code changed, of course, because the content changed. And then it closed the revisions, and then it closed the page. Yes? I will show you this. So this is what that file is, or at least a piece of it. So each tag has an open tag and a close tag. So this is opening, this is closing. And every time you open it, you have to close it. So they always have to match. These are all so when you open the file, the stub meta revision, it has a header. The header defines all the namespaces that are available in that edition. Namespace 0 is the regular pages that you want. Namespace 1 is the talk pages, so it's the discussion about those pages. And then you have talkspace 1, 2 is the users, 3 is the user talk. So the pattern is always the same. Even numbers are the actual pages, odd numbers are the talk about those pages. So they always alternate like this. Right, so you have portal at namespace 100, portal talk, namespace 101. So the talk is always +1. And here's the definition of what all of these things mean. And you can see that the pattern is correct. Yes, and this is the rest. So this is the actual file I just showed you before. So it's starting a page, closing a page, and then this will be a sequence of these in the file. Right? For this page, these are all the revisions, and then this page, all the revisions. And you can see basically all the information I showed you before already. The model is wiki text, the text ID is 115, whatever that means. The hash key is this. So this is basically all the information you saw before. So if you wanted to extract the article revision information into a CSV file with this format, using this file, so something that looks like this, which is kind of what I just showed. One thing you have to pay attention is that there are 3 ID tags. Right? So the meaning of the ID tag depends on where you are in the hierarchy. It can be a user ID, it can be a page ID, it can be a revision ID. So you have to keep track of where you are, which makes things a little bit tricky. Like I said, basically you are defining a finite state machine, and you're keeping track of what state you're in, and if that's the information you want or not. So I'm doing this in a very stupid way. There's more sophisticated ways of defining finite state machines properly. So that's the page ID, that's the revision ID, and that's the contributor ID, like I was saying. And in XPath, this looks like this. So I'm defining a bunch of fields, or rather a bunch of variables that I'm going to use, a bunch of fields I'm interested in. For each element, for the start element, this is how I'm keeping track of where I am in the files. Oh yeah, still have plenty of time. This is what the end element looks like. So basically, if it's in fields, so it's one of the fields I'm interested in. If the name is an S, means it's oh, thank you. It's the namespace. So if it's 0, it's an article. It's an article means it's good because I'm only interested in articles. Then if the name is timestamp, then that's I'm assigning it to the timestamp. If the name is an ID, I'm checking if it's a page. Then it's the ID of the page, so I put it in the page ID. And if I'm no longer inside the page. If not, I check if it's a contributor. If it's not a contributor, then it's a revision. And if it's not a revision, then it's a contributor. Right? These are the only two options. Then now, if the name is revision, I'm checking it is a revision of an article, because like I said, I'm only interested in articles. If not, I'm checking if it's a page. If it's not an article, it's there. And if it's a contributor, then it's on the contributor. So I'm switching all of these things. And the chart data function is always very simple. You're just grabbing the data, putting it in the buffer. That's it. Right? You don't care anything about anything else. And then the rest is just the same as before. You create the parser, you overwrite the methods, and then you print out output. So here I'm just printing out basically column headers, and then this will print out one line for each revision in that file. So let's look at Wikipedia revisions. Actually, yeah, I forget which file I wanted to look at. Where's the cursor? Here it is. Oh yes, the meta history. That's easy. Did I forget? No, Wikipedia revisions, yes. And here you go. So you have the column headers over there, and then page 1, revision 1, revision 1028, 1029. These are the different timestamps, and this is the title of the page. And you can see it basically doesn't change much. But if you scroll down, then you can see that you have different pages. The name can sometimes change it. I don't see an example here. And the pages can be edited over a long periods of time. Right? Like this one, for example, was edited between 2009 and already 2011, so over the course of several years, and all the way down to 2015. Now, back to the original problem. We have these language links, we have these IDs, we have these titles. How do we match these things? This is not necessarily a trivial task. The only place where the two fields appear together is in the revision files. So this is the only place where you have the ID, the page ID, and the page title. Everything else uses either the title or the ID, so you necessarily have to go to the revisions file. But we already saw how to process those. Even more fortunately, the Wikipedia Foundation also makes available the stub meta current, which is similar to stub meta history, but gives you only the current version of the page. So if you're not interested in the revisions and now it's changing over time, you can look just at the current one. This means it's much easier to download because it's much smaller, and it's also much easier to process. And of course, you do this in two parts. You convert, as usual, download the XML, convert it to CSV, and use the CSV to match the titles in the other CSV of the language links for the page ID for the Wikipedia edition. Right? So this seems a bit complicated, but let's see what the code looks like. I think I'm almost done, actually. Yes. So here I'm opening the language links. I'm grabbing the header as before. Because I'm only looking at one language just for simplicity. So if I'm looking at the link into that language AB, then I'm getting what is the key. So I'm looking at what is the from page and then matching it there. So I'm basically creating a dictionary for all the for a list of all a dictionary of all the IDs of the original pages. So the title of where the key is the title of the destination page, and the value is the key of the original page. Then I'm opening the other file in the other language. So now this is the AB language, which is the one we were looking at there. So I'm trying to create the links between this language, ACE, and AB. So I'm looking at the language links of ACE. This gives me the IDs for that one. Now I need to find what are the IDs for the page titles in the other language, right? So now I'm going down this. Again, I'm reading out the header. I'm grabbing the title. If the title is one of the titles I'm interested in, this is why I'm indexing here by the title, then all I have to do is is basically print out what is the ID for that page in this edition, and then says this page in this language as this ID is pointing to this language to this ID. And here I'm hard coding the file names, so I can just go quickly through them. I don't need to worry about doing it, so I can just do. Yes. And poof. And now you have all the connections. So this page in this edition is linking to this page in that edition, and you can see all the links. I'm filtering also. Rather, here I'm not filtering by any type of namespace, so I'm printing for all the pages and all the editions, in all the namespaces, and just going down. For simplicity, I'm doing just one language, one example. You could do this for multiple languages. You have to download multiple files and handle them separately. So maybe do them one by one, and keep different dictionaries for them, and that would work. And that's it. So if you have any questions or insults, I'm more than happy to answer them. Rotten fruit is also good. If not, I think we're done. Thank you. I understand this was a bunch of different things, but I'll make sure all the files and all the examples are in the GitHub.